So here we go. Welcome everybody. Welcome to our Senior Projects Fall 2020 virtual presentations. I see a lot of smiling faces or anxious faces, but I think all the teams have pre-recorded video, so nothing to be nervous about. The only thing you really have to worry about at this point is getting grilled with questions from our faculty, Dr. Razavi, Dr. Zhu, Dr. Gamari, Professor Greiner, Dr. Mu on the call. So, I don't think they're going to purposefully ask you questions you can't answer. They really just want to get to know your projects and make sure that you've thought about different things, especially for the Senior Projects 1 teams moving into next semester. So, all right, I'm going to just briefly share my screen and show you. Here's the great poster, as always. Thank you, Lisa, for coordinating, creating this poster and getting it up in the hallway to advertise our event. Thank you to the teams for creating their logos. I think very unique logos and very unique projects in general. I think all our guests, faculty guests, will enjoy this. Here's the schedule we're going to adhere to. I think we'll be fine sticking to the time. I'm going to have my timer on my phone just to make sure that we stick to it. But I think having each team pre-record their video, I told them to stick to 9 to 11 minutes for their actual presentation, and then that'll allow us 3 to 5 minutes for questions. I'll sort of be moderating the questions and making sure we have to move on. So, if we're getting close to the time for the next group to start, I'll say, okay, last question, and then we'll start. So, okay. A couple, one more thing to mention, when you share your screen, everyone should see at the bottom middle, it says share screen. So for those that are in charge of playing the video, especially if you have sound, make sure when you share screen, there's a little tiny button on the bottom left that says share computer sound. So I know we had our ME384 presentations this week, and a lot of groups were getting hung up on that, and they were wondering why their sound wasn't playing. So just make sure when you share your screen, you hit that little tiny button that says share computer sound before you hit share. All right. Actually, this is a pretty quick welcome as compared to our in-person years. Does anybody have any questions before we get started? This is in the spring, we had our first time running a spring-fall sequence for Senior Projects. So this is going to be our first fall Senior Projects 2 cohort going through. So I'm going to start with all the Senior Projects 1 teams from that schedule, and they're all in order, groups 1 through 9. And then we're going to be going to the Senior Projects 2 teams. I'm going to share my screen just one more time so you can see what I'm talking about. As soon as I'm done blabbering on, we're going to get started right with Senior Projects 1 team. I tried to have the start time, end time, what Senior Projects class they're from. Here's their description, their groups, their team name that they chose, as well as a brief project descriptor, just a 1 or 2 sentence project descriptor. So we're going to have, it works out nicely, we're going to have 4 teams first, then a quick 5-minute break, stretch. And next 4 teams go, another quick break, and then our last 3 teams, and then a conclusion. And then we should be done by 4, quarter after 4, somewhere in that range. Okay. All right, everybody. So I think you're going to enjoy our groups. I've watched them present 3 times each throughout the semester in class. So I'm going to try my best to refrain from asking questions. I'm going to give my colleagues that haven't seen their projects yet an opportunity to ask questions. So all right. Let's see. I'm gonna mute all non-participants. Oh, the last thing, I sent an email to all the Senior Project students just requesting that when it's your turn to present, please unmute yourselves and unmute your camera so that we can see your smiling faces as we ask you questions. So it's easier to ask you questions if we can see you. I know there was maybe 1 or 2 students that said, no, my camera really isn't working. I'm having technical difficulties. That's fine. But if you do have a working camera, just kindly ask that we could see who you are. If you want to mute your video while the other presenters are going, that's fine. I think it does save bandwidth for Zoom. Kind of makes logical sense that it does. So, all right, we're 3 minutes early, but let's just get started. So I'm going to ask group 1 Recycle Thermoset Plastic to start us off, please.
I will start sharing my screen, and if the sound is not clear, please let me know.
Okay.
Hello everyone, this is the Recycling Thermoset Plastic Group 1. I'm Mohammed Banasir. My team members are Abdullah Shreem, Saad Shamani, Hamid Rawali, and our advisor is Dr. Mo. For the agenda, we will be covering introduction, requirements, specifications, materials, method, budget, WBS, schedule, and future plan. Thermoset plastic is kind of plastic that cannot be disposed of or recycled easily. That is why companies tend to produce more of it instead of recycling it. Furthermore, plastic ends up in landfill, and it takes up to 1,000 years to decompose in landfills, and that will cause two negative impacts on both environment and economical. On the environment, worldwide 380 million in 2018, and from 1950 to 2018, plastic of about 6.3 billion tons have been produced, and there is only between 9% to 12% that was recycled from the productions. The rest of plastic either is still being used until nowadays or ended up in the ocean or landfills. Researchers suggested that by 2050, the ocean might contain more plastic than fish in terms of weight. Also, more than 260 lives in the oceans have been stuck or trapped in plastic disposal. Also, in 2015, 133.9 million people suffered from unhealthy levels of air pollution.
For the economical, plastic pollution damaging the economy by $13 billion because of affecting the fishing industry and cleaning the beaches from the plastic. Recycling plastic takes 88% less energy than making plastic from raw materials. By recycling 1 ton of plastic, we save 5,774 kilowatt of electricity, 685 gallons of oil, 98 million of energy, and 30 cubic yards of landfill space. For the requirements, we have three main points. The first one is reduce the plastic production. Second one is reduce plastic waste and reduce the negative impact for both environmentally and economically. For the specification, thermosetting plastic are known as cross-linked and cannot be recycled easily. Researchers suggested the three technologies to recycle thermoset plastic: mechanical, thermal, and chemical.
As this slide showing, the three technologies are used to recycle thermoset plastic: mechanical, thermal, and chemical. In our experiment, we'll be using the mechanical and thermal technologies. For the mechanical, we'll be using pulverization. For the thermal, we'll be using the combustion. As you see here, the list of the materials and equipment we'll be using in the lab: Pripol, DGEBA, zinc acetate dehydrate, and the equipments are round bottom flask, vacuum desiccator, PTFE beaker, 10 cm in 10 cm in 0.15 cm brass mold, anti-adhesive silicone paper.
As this slide showing the formula for the thermoset plastic, the left side picture showing how the molecules in the thermoset plastic structure connected with a cross-linked, and that's what makes it really hard to recycle it. And it's not like the thermoplastic. When it's exposed to heat, it's melt, and we could inject it easily and recycle it with so many different ways. But with the thermoset plastic, when it's exposed to heat, it harden or it burn. The right side picture, it shows the structure for the thermoset plastic, and the thermoset plastic are formed by condensation, polymerization, and they have three-dimensional cross-linked structure. Our method gonna be divided to two parts. The first part is preparing the sample and then recycling and reprocessing. To prepare our sample, we will have to make 3 solutions of fatty acid with different concentration of zinc acetated dehydrate. For the purpose, we will have to add 20 grams of fatty acid in three round bottom flasks and label them. Then catalyst at different concentration with 0.17 grams and 0.922 grams and 1.76 grams were introduced in 100 milliliter round bottom flasks. Then the temperature will be gradually increased, starting from 100 Celsius up to 180 Celsius, while maintaining the mixture under vacuum. Evaluation of acetate acid indicates that the fatty acid replace acetate as ligand of zinc. And then we will leave the sample in 180 Celsius under vacuum until gas evaluation is dissolved and catalyst particles were fully dissolved within 2 to 3 hours. Then we will have to add 15.75 fatty acids mixture in the beaker on around bottom flasks. Then add 9.25 grams of DGEBA in mixture. The mixture will be heated to 130 Celsius until phase became miscible. For the final step for preparing the sample, we will stir the solution manually, then quickly pour it in mold sandwich with an anti-adhesive silicone paper. The mold will placed in heated and pressed and left for at least 6 hours at temperature 130 Celsius. After that, our sample gonna be ready, and then we will have to do the recycling and reprocessing. The methodology that we will follow for this step is for the recycling step, we will pulverize our sample and make it into powder. Then we will combine it by applying pressure. The combined powder is heated under pressure. Due to anti-bond exchange reaction, the polymer particles will be welded, interface will disappear, and this process will be repeated several times.
For the budget, we have 7 materials and equipment needed to complete the project with total cost of $298.74. Purple 1040 is provided for free from Munich Company in Peterson, New Jersey. The DGEBA costs $55 for 500 gram. Zinc costs $81 for 500 gram, and we need to round bottom flux for $39.18. Vacuum desiccator is for $78.67. The PTFE baker is for $19.89, and the silicone paper is for $25. For the WBS, we break down the project into 7 tasks, as you can see. However, the 2 main tasks is the 1.2 research and methods, because we spent much of this semester doing the reading research, trying to find a method and comparing the methods we found. And for the next semester, our main tasks will be the experiment 1.4. So I will discuss it in the schedule. In the schedule, we accomplished all of the assigned tasks for this semester. As you can see, we assigned the due date and start date for each tasks. And as I mentioned in the WBS, for this semester, we assigned much of the time for the research and methods, which about 2 months. And for the next semester, much of the time is assigned for the experiment. For the experiment, we assigned about 2 months because the experiment is divided into actual 2 tasks. So we will need to prepare the sample and to run the recycling experiment. So we assigned much of the time to give us some space if we make any error or if we need to do more than one experiment.
Our future plan will be ordering the materials and getting familiar with the lab equipment. This is our references, and this slide showing the budget references.
Okay, thank you guys. So I'll open up to our ME faculty if you have any questions for this team. Dr. Razavi, I think you're muted.
Guys, wonderful presentation. I didn't get the relationship between fatty acid and then cross-link structure. Is the fatty acid is going to open up the cross-link structure?
Yes.
Do you have the equation of action that you can describe that?
The equation of the reaction, I actually don't include it in the presentation.
Is it? Okay.
I didn't include it in the presentation.
Oh,
This is the only formula that we include.
Can you elaborate on what type of fatty acid opens up the cross-link structure?
I don't have that right now listed, but
that's fine. Thank you.
All right, I have a question for you guys. These look very much like a chemical engineering project, if you guys agree. My concern is just that there are many things you learned in mechanical engineering you are not applied in your capstone project. I also have, I guess, 2 specific questions. That's a general comment. The first one is, you guys mentioned the main work in the first semester you did was research methods. So I would like somebody to tell me what are the methods you researched. You have to spend like an entire semester to just try to research the background methods. And so I really, because if that's the only thing you did in the first semester, I would really like to find out what are those methods and what are the pros and cons of each method.
Dr. Zhu, wasn't all the time the 2 months that we were looking for the method, but what make it...
but that's what the presenter said.
Yes, yes, but what took us more time is trying to find a method that we could we could do in the labs with the limited budget and limited resources. So that's what make it hard. We found so many methods, but we couldn't apply them. And
so be more specific. What are the methods did you research?
Like the name of the method?
Yeah, I mean, you say you research several methods, right? What are the pros and cons of each method?
Well, some other methods that they used high technical machines that we don't have in the lab. So
that takes you like 30 minutes to get rid of that method? You see what I mean? Because we don't have a machine. I mean, is that really takes such a long time to debate?
It's not taking much time to debate. It's each method we evaluated based on.
Okay, so since you mentioned that, maybe you could answer this better. So tell me, what are the methods you guys researched?
Actually, we came up first with the FOR method, and we start to compare between them.
What are the 4 methods?
The first 2 methods was using a special machine for pressure and injection. So we couldn't go with that. We dropped this research. and we move on with the second research that shows us we can go with the grinding and turning the thermosets into powder. But the other method is need maintaining the material under vacuum and under heat for a very long time. One of the material was in the under the heat for about 2 days. So we thought that would be hard to maintain the same heat degree and pressure for a very long time, and we keep maintaining this. We drop it, and the last method was the best for us that fit our budget, and we can succeed do it in the lab.
So which one is more widely used in industry, most feasible?
Last question, please. Go ahead.
No, I have one more point, which is this is a chemical. You are going to deal with lots of chemicals, so that's it will be very difficult for you because we may not even have those kind of environment for you to create this kind of experiment.
Abdullah, can you go to slide 8?
Sure.
Yeah, I think Dr. Zhu has a great point that as you move forward for the next semester, you need to focus more on the mechanical method to make your whole goal happen. You said you want to recycle these thermoplastic, make the mechanical method to make it happen. I think that's along the lines of Dr. Zhu's point. But yeah, please answer the last question, and I got to move on to the next team.
Yes, actually, as you see in the picture, the method we are using is like we're using 3 technologies here to come up with the recycling experiment. The first thing we're gonna use the mechanical. We're gonna grinding the material, and we're gonna use the combustion, and we will apply chemical. So it's not only chemical we are going to use.
Okay.
This, if I may, so this is more like a research than mechanical design. So the focus of this project is more towards to the material science part. That I agree, but I would like to try to ask our students to think about how to combine or couple the chemo-mechanical part and focus on more on the material side other than the machine side. So that's the that's something that I sort of like want to have our students to think about when they work on something for senior project. It's not always has to be a machine, but it can be a technology can be a synthesize. And so they actually spent some time, quite a lot of time to study different methods. And to answer Dr. Zhu's question, none of these methods have been used in industrial. None of them. They are in laboratory only. And the thermoset materials that they are going to fabricate, synthesize next semester, they are special type of thermoset. So it's not like a commonly used thermoset material that can be recycled. So it's not, we're not there yet. So so I also have the concern, like this is a project more like to our material science engineering, those students when they are there. So yeah, so that I agree. So later on, when they have the material synthesized, they actually, the recycle part, they need to ground it. They need to have a mold and apply pressure and put it in the hood in the oven. Those parts can be related to mechanical, sort of. And they did spend some time to find out what is the best method that can be achieved in our lab. And now this paper, they found that, and I agree that we should be capable to to finish everything in the lab.
Ed, can I interject here?
I need to move on, Dr. Brazil.
Just 10 seconds, 10 seconds.
You got 10 seconds.
Okay. If they come up with the chemical degradation of the cross-link structure, that this polymer could be disposed easily, that would be remarkable innovation.
Okay. All right. Thank you very much. Thank you very much, guys. I'm going to give you a virtual clap. I know my students know how to hit the reactions button on the bottom right if you want to do a virtual clap. Okay, so we're moving on to group 2, Davy drones.
All right, so all right. If you can let me know.
McCoy, did you share the audio when you shared your screen?
Working on it.
Okay.
Sorry about that. All right, we should be good. Hello everyone, we are the Davy Drones Senior Project Group. And this is our final presentation for the semester, detailing what we did this semester and what we will do next semester.
Our project that we created is an underwater autonomous vehicle that can view damage on underwater structures or the hull of a ship in order to detect wear before any major failures occur. The drone will follow a predetermined path using a passive buoyancy system to allow the drone to submerge underwater. It also uses 4 propellers, 2 of which will use a motor to control the pitch angle. The other 2 will be used to provide upward propulsion.
Structures that lie below the surface of water have become integral to certain parts of society. These structures often become damaged due to erosion and continual force of water running on them or debris. The visibility of these underwater structures is severely limited, meaning most of the damage goes unnoticed for long periods of time. When the damage becomes severe, the entire structure must be repaired or replaced. If the damage could be caught or repaired before they propagate to this point, there would be less need for large repairs and inconveniences to the public.
So the methods we'll be using for the drone are detailed in this overall system block diagram. So firstly, the drone will be placed in the water and then activated. Then the drone will submerge using the moon pool mechanism that we have to allow water to fill into our chamber. So the upper chamber of the drone will fill with water, and then the drone will be able to sink. So once the drone has sunk, the drone can move autonomously underwater. And once it's done moving underwater, however it wants to move, the drone will resurface using all 4 propellers to provide upward propulsion. And then as it sits at the top of the water, the upper chamber will empty as the drone breaches the surface with the solenoid valve at the top open so that the air can fill back into the top of the hull. Then finally, the drone will be retrieved. So the main theory of the project that we're working on is Archimedes' principle. That was how we were able to discover how much weight we needed to submerge the drone and how we'd be able to move underwater. So the figure 2 here shows how the buoyancy force acts on an object that is submerged underwater. So the way that we're looking to overcome the buoyancy force is to allow water to fill into the upper chamber, which will add to the weight of the drone. And then once it has reached the weight to overcome the buoyancy force, the fill will shut off and the drone will be able to submerge. And once submerged, because we can't stay at a constant height, just by having it in the water, once it's submerged, it sinks. The drone will keep at height using the 2 front thrusters for a low pulse propulsion constantly as we're underwater.
Figure 3 shows the full assembly of the design with the 4 thrusters, the rear ones that will rotate for an upward orientation or a forward orientation. The hole at the top of the hull is connected to the solenoid, which controls when the air is released to flood the top of the hull. Figure 4 shows the bottom assembly with the 4 thrusters, thruster mounts, the servo motor that controls the pitch of the rear thrusters, along with there's also the channels that channel the water from the holes in the bottom of the hull to the top half of the hull where the water chamber is. Figure 5 shows the mid plate of the hull, which seals the bottom of the hull so that no water leaks into the electronics.
So this is the thruster that we chose. We decided to buy a thruster ahead of time so we could do some testing. The brushless DC motor requires 12 volts and 20 amps to function. We will use 4 of these thrusters, 2 of which will use a motor to control the pitch of the angle. The 2 rear thrusters. The other 2 will solely be used to provide upward propulsion. So these are just the top view of the thruster, where you can see the propeller, and the bottom view where you can see where the wires come out. The white stuff is the sealant to ensure that it's waterproof. We are also using an electronic speed controller, an ESC. It is a device that regulates the flow of current into the motor to allow it to connect to a DC power source. We will be using it to change the speed of the brushless motor. We also will be using a solenoid valve. In order to have the drone to stay submerged, a chamber in the upper half of the hull will be able to fill with water to add weight to the drone. The air in the upper half of the chamber will be released through the use of the solenoid valve. Upon being placed in the water, the solenoid valve will open, allowing air to be released from the upper chamber and the water to flow into it instead. You're going to stop the record.
Moving on to the management portion, take a look at marketing. Different avenues have been explored for potential investors and customers. Government agencies are a strong match for Davy drones. At the state level, construction and repair efforts on public bridges and underwater pipelines provide a constant need for specific work tools. Funding is usually approved through the use of taxes, providing a fairly constant availability of money to initiate such repairs. At the federal level, military and defense efforts are always in search of new innovations and tools to aid with their efforts. Davy drones can adapt to help with their underwater operations by adding a camera to the drone or possibly weapons. Davy drones can capture a share of this marketplace by ensuring a reliable and durable design at a reasonable cost, while making sure to showcase its innovative drone technology specified for underwater use. Another area of focus for sales could potentially be the public consumer sector. This includes residential use for hobbyists and enthusiasts. Different models of Davy drones can be created, a more rugged and larger design for government use, along with a lighter compact version for hobby use. Many people enjoy exploring or filming using an airborne drone through the use of a camera. Similarly, there could be many who would like to expand their filming to the underwater realm as well. Aquatic life could be observed along with debris and objects that lay at the water's bottom. These buyers can be reached through online advertisements and by making Davy drones available on popular RC hobbyist supplier websites. Our deliverables, the work breakdown structure has been successful in subdividing project work into smaller work elements. The scope of the project has remained consistent with a clear end goal. The project schedule is being followed and has Davy drones planning for next spring's work in advance. This will ensure a smooth transition in the construction and testing phase of the project next semester. Taking a look at our budget, we have a total Wilkes cost of $318.98 because we were able to use some spare parts. Otherwise, it would be $343.97. Here's our work breakdown structure, consisting of 4 main branches of mechanical, electrical, testing, and management. Here's our full Gantt chart for the schedule. Here's a closer look at it. Continuing on and further. That's all of it. Risk management. The whole design is crucial to the success of the drone operation. It is recognized that underwater behavior and handling is hard to predict without trial and error. Alternate hull designs have been discussed in the event there is an unforeseen flaw in the current model to mitigate lost time later on. An unforeseen opportunity is a possibility that the drone performs exceptionally well. Components such as the battery and motor sizes could be decreased to exploit weight and money savings. Finally, change control management. Any problems that arise are reported to the team as a whole. They are then discussed as a group in order to maintain a unified focus and understanding of the project direction. Records of design changes are made to proper documentation upkeep. In the event there are difficulties or performance issues with certain components, Alternate brands and styles have been researched and can be quickly obtained for replacement. Our construction plans. In the months leading up to the next semester, the plans to begin 3D printing the whole of the drone with a personal printer. Supporting pieces will also be made, and once the whole is printed, a proper plan for sealing the two halves of the whole will be better formulated.
So for testing, as a continuation of this project, next semester will consist of all the testing to be done on Davy drones. Now, for testing, we have several different types, which include stress testing, waterproof testing, hydrodynamic testing, movement testing, and simulated testing, which is the testing of the code used for the autonomous movement. The first stage of movement testing was done and will be shown on the next slide. So preliminarily, we tested one of the thrusters that we got, and the videos below show a proof of concept of how the thruster moves and of how it can throttle up and down to control the speed. So the first video we have here shows the movement of it connected to a wooden board, just as a proof of how it can move. And obviously the wires inhibited the movement a bit, but it seemed to move pretty well. The second video shows the throttle control of the potentiometer.
So in conclusion, our design right now is finalized and it's ready to be built and tested next semester. So far, we have figured out how to control the speed of the thrusters using a potentiometer. The next step is to use the program on the Arduino to control the speed and the pitch of the rear thrusters. Any questions? So in conclusion, our design is finalized for this semester.
Okay, yeah, I think we're ready for questions for this group.
Ed, can I ask you a question? What is Ed?
Yes.
What is the size of the hall?
Go ahead.
The hull is about 14 inches long and about 5 inches wide, or in diameter.
How does it navigate? Do you use, are you planning to use GPS?
Currently, the plan that we have is to figure out about how long it will take to move from one point to another in the water, and then set timers for that. If we get into a deeper budget, then maybe we'd be able to put GPS or something like that in there. But for now, we're just working with timing.
Very good.
From point A to
Thank you.
This is Dr. Razavi. How do you submerge and then come back to the surface? What's the mechanism there?
So the way we have that set up, we have moon pools on the bottom, which are just holes in the bottom of the hull. And then we have a solenoid valve up top that will open to release the air that's inside of the hull, so the water can then fill up into the hull, into the upper part of the hull. Once that's happened, then the drone can submerge, and from there it'd be able to move underwater. Then when we want to resurface, we would have the thrusters go moving upward and then sit at the top for a bit to let the water drain out so that it can return to the buoyancy to sit at the top of the water.
That mechanism has to be a little bit more explained. Thank you.
I think we have time for one more question. Anyone else wants to weigh in?
I have a couple of questions and maybe a couple of comments. One is that the two front thrusters are controlled using a servo motor, right? Can anyone hear me?
Yeah. No, you're muted.
Oh, okay, I was wondering, maybe I'm muted. Okay, no. So the front thrusters are controlled using servo motors, right?
They're rear ones.
The rear ones, yeah, the back ones.
So, or the back one, I don't know. How are you going to provide sealing for that? How are you going to seal? Is it just using gaskets or O-rings?
We're using an O-ring material around
sorry. If we're using an O-ring material, it'll be around the whole hull. Have like a little, what do you call it? Like a place to put it around the hull.
But I'm talking about the shaft that controls the thrusters with the servo motor. I mean, there's an opening there.
Yeah, so the plan is to try to use like a oil, in motors they have like a oil seal that goes around the axle that keeps the liquid inside. So we're planning to use like a rubber seal that fits tightly around the axle and then sit into like a groove in the bottom of the hull. That way, and then we can kind of.
So what I see is that for the next semester, there is a lot of details that you need to work on. It's just way too much detail you have to work on. And your schedule, your Gantt chart, you just stopped it like for 5 seconds. There is nothing for you for the winter break. Are we gonna go to holiday, all of you guys, for 1.5 months?
No, and I don't think it's reflected on the Gantt chart. We sort of decided this after the Gantt chart was made and the schedule was made, and it hasn't been updated since, but we're going to be.
And that's not just a comment for you. I'm telling that to everybody, like every group. Forget about going to holidays. I mean, maybe take a break for 4 or 5 days after your final, seriously.
Yeah.
I mean, the progress is already terrible. I see my groups, everybody's because of the corona. And if you're going to do some research, computer modeling, take advantage of this 1.5 months. I mean, you cannot say, hey, it's not, there is no holiday, guys. You have to work. And the last comment, the solenoid valves, if that's something that I know from Amazon, you bought it for like $10, $15, they are crappy. So make sure, because that's a critical part. We had purchased a couple of them for my research, the plastic body, the brass inside. You need something really reliable for that. So be careful about ordering your stuff, because this thing is going to go underwater and there's going to be electronic and you're going to protect things. So it's much different things that we're going to design.
Okay. Thank you, Dr. Gamari, and thank you, team. Great job on your presentation. And yeah, I also echo Dr. Gamari's comments that there is no break. Yeah, I think all the teams need to move forward. So let's move on to the next team. So we're on to Group 3, RoboPharm. And while that team's loading up, I just want to make another announcement, please. If all the team's leaders can upload their PowerPoint to live at your earliest convenience, please. Perhaps during our first break, that would be good. I know all the presentations are done. Just make sure you upload it to live so I have access to them. Okay, yeah, let's move on to RoboPharm.
Hi, my name is Hannah Klaproth.
I'm Alex Abad. I'm Justin Whetstone.
I'm John Seasock.
And this is our final presentation of our product called RoboPharm. Here is the final design for semester 1. On the left, you can see our 3D design of the internal processes and frame. On the right, you can see our prototypes so far of our internal processes with a much less complicated frame. Here is some background information and statistics to justify this product and why it needs to be on the market. There are approximately 138,000 medication errors a year because of errors in the prescription dispensing and preparation process. Pharmacists are consistently a limited resource in a pharmacy because of the large amount of tasks that are required per day, such as verifying prescription information, checking for drug interactions, and contacting insurance companies. Pill counters are available, but they must be manually loaded per pill type and can cost anywhere from $2,000 to $4,000 per pill counter. Here are the deliverables of our product and what we want it to accomplish. The pill hoppers are able to release 1 pill at a time. Pills are counted and dispensed correctly using a load cell and LED light sensor. The filled bottle is transferred to the packing carousel. The packing carousel twists the cap onto the pill bottle. and then the packing carousel dispenses the pill bottle out of the machine.
So to control the machine, we are using Arduinos to control the stepper motors and servos along with any LED or photoresistor. The Arduinos are going to be hooked to a Raspberry Pi. The Raspberry Pi will control all of the GUI interface and all the data for the pills. The data will be kept in a database on the Raspberry Pi. It's going to be coded in MySQL. It'll hold the pills inside the machine, all the pills that could possibly go into the machine, and keep track of the count of the pills inside the machine. Therefore, if a prescription of 30 needs to be filled and the hopper is only holding 20, the program will know that the prescription could not be filled.
Here is our budget breakdown. We've broken it into a couple different categories. So our frame, and then there's our internal processes, dispensing, transfer, and packing, as well as electronics and hardware. All of the things in orange are 3D printed parts. We've purposefully kept a lot of our parts 3D printed to keep cost as low as possible. After all is said and done, it seems like the cost is going to be $673.95. Here is our WBS breakdown. At the top, we have the name of our project. We've broken it down by product stage. So in 1.1, we left documentation by itself because of the unaligned due dates. For 1.2, we have our design and then all of the parts breakdown from that. Then we have our prototyping, programming, and then our final assembly, which will be mostly in semester 2. This is our schedule breakdown. Under RoboPharm, we have documentation. All of these dates were taken directly off of the syllabus. Our design phase, we had an internal deadline of October 23rd. Our prototyping, we just finished Friday. Our programming, we plan on doing a lot of that over winter break, and then final assembly will be the bulk of semester 2.
So my main focus was the pill dispensing. This included the bulk storage of the pills, the pill dispenser or the hopper, and the counting of the pills using a light sensor.
I'm in charge of the transfer arm sub-design, which includes the theta Z movement, a second verification using a load cell, and the transfer of a filled pill bottle to the carousel.
And I'm in charge of receiving the pill bottle out of the transfer arm, the rotation of the carousel, and the tightening of the cap onto the bottle.
This is the pill hopper 3D design. It includes a lid, an outer housing, a DC motor, a sifter, and an inner. If we take off the lid and outer housing, we can see the sifter. The sifter has a hole in it in which exactly one pill fits into. This sifter rotates via a DC motor embedded in the inner, like this. The inner is curved to push all the pills to the outside to fit in the slot on the sifter. The outer housing has a hole in the bottom in which the pills will fall out of. The prototype used capsule light candy to simulate pills for our testing. Each hopper can hold 520 capsules. Each hopper will hold a different kind of pill, and when the pill is chosen, the correct hopper rotates above the bottle. A photosensor turns on and counts the correct number of pills and stops the system once the prescription is filled. A NEMA 17 stepper motor was used to rotate the carousel. It's attached to a 4:1 gear ratio.
This is the transfer arm design. It consists of a carriage with a transfer arm. It is moved vertically by a stepper motor guided by 2 linear rods. The transfer arm rotates 180 degrees by a 180 degree servo. There is a load cell underneath the pill bottle. They'll act as a second verification with the light sensor. to make sure the correct number of pills are dispensed into the bottle. After the bottle is filled, the transfer arm will rotate to the other side to the packing carousel. This is the movement of the transfer arm. The threaded rod has 16 threads per inch, and the stepper motor uses 200 steps per 1 revolution. So using these numbers, we can accurately calculate the vertical position needed to place the transfer arm properly underneath the correct hopper.
This is the packing stage. This is the final stage in the process before the pill bottle is dispensed. The carousel will take the pill bottle off the transfer arm and rotate through stages. The stage that is shown here is the cap tightener. The pill bottle will sit in this, and this will rotate through a threaded rod, and it'll push the pill bottle up into this platform until the cap is tightened. As you can see, the pill bottle rotates out of the transfer arm by the carousel and gets ready for the first stage, which would be the cap tightener.
This is our testing plan, which includes notch fatigue testing, which will test the notches on the carousel where the bottle goes. Stress testing. On the process of the carousel that tightens the cap, the bottle is pushed into the cap and twisted on. Physical testing. Tightening the cap on the pill bottle where the servo is used. Gear fatigue. Testing the life of the gears. Cycle life. How long one cycle takes. Operational test, testing how long the machine can run without any errors, and a dispense test to see how well the hopper dispenses 1 pill at a time.
Our plan going forward, over winter break, we are making design improvements based on prototype testing. We're going to work on the GUI interface for ease of customer use and develop additional pill size inserts for the pill hoppers. During the spring semester, we plan on adding mechanical processes for pill bottle and cap refill, work on the internal process cohesiveness, finalize our prototypes so that it completes multiple process cycles fluidly, and adding other capabilities such as a label printer and putting the label onto the bottle.
Big shout out to Dr. Zhu for helping us go above and beyond to help us achieve our goals for the semester. He really kept us in line and not trying to overdo what we're trying to do in the amount of time that we were given. Also, a huge thanks to Dr. Ben-Nars for giving helpful feedback on our progress throughout the semester.
And these are our references. Anyone have any questions?
Yes, I do. This is Dr. Azavi. How many prescriptions this unit can accept?
Our original prototype is designed for 8 different pills.
Okay, great. Then I'm a physician. I send the 8, orders to you, and then how they recognize that between aspirin and heart problem or heart medicine that they are smaller, perhaps. What is the recognition mechanism? Yeah.
I don't think I understand the question. Are you saying like, how's the machine know?
The solid drug is not all coming in the same weight and same size.
Correct.
How do you differentiate those?
The insert and then the outer housing or the sifter changes based on the general pill size. The data for the mass and the quantity will be kept in the database. So that way a lighter pill would have a lighter mass. Therefore, the load cell would know that it's per 30 prescriptions, it's going to be a lighter weight.
Are there similar drugs in the market that this system could be confused?
Like 2 different same size pills?
Yeah, and same density.
There definitely could be, but the pharmacist will input the pill into the machine in the correct location. So if the pharmacist doesn't put the correct pill in the correct location, of course, the machine would not fill the correct prescription.
Then you need the pharmacist to sort it out and put it in that machine.
Yeah. A pharmacist will definitely have to load the machine.
Thank you.
Mm-hmm.
Any other questions for RoboPharm? You guys must have did a really good job explaining it. There's no questions from our faculty.
Well, just maybe one thing that kind of kept me thinking. So
Yeah.
in the process of switching between different, for example, let's say it's on like a tablets, for example, if there is any residue, is there is a possibility of residue from any of the tablets if something breaks, for example, any possibility that from the previous prescription something is stuck somewhere and then goes into someone's bottle?
Yeah, so the way it's designed is that each hopper is unique to pretty much that pill. So, and then we're using a light sensor to count the pills in the bottle. So we're trying to eliminate the cross-contamination factor. And by measuring the mass underneath the pill bottle, none of our components should touch the pills other than the unique hopper itself, which when a different prescription would want to be in that position, that hopper would be replaced with a new hopper. So there's no cross-contamination.
Thank you.
Yeah, I have a question if there's time left. Notch fatigue testing. Where are you going to do notch fatigue testing?
That'll be done on the carousel part. I don't know if we could show it, but on the carousel where the pill bottle goes in, there's little notches there to hold the pill bottle in so it doesn't fly out. So what we were going to do is just like put the pill bottle in a bunch of times because it is 3D printed. So it could wear out over time. So we were just going to test how many times the pill bottle can go in and out before the notch would fail us.
How do you want to test it? Are you going to actually evaluate the number of the cycles that this design would take?
Yeah, it would be like a manual test.
Manual test. Okay.
Yeah.
How much load you are going to apply there?
How much load?
Yeah.
We didn't really measure the load because the pill bottle and the pills are really light. So there should really be no stress that would be placed onto the carousel.
So there is no fatigue failure there.
Oh, fatigue failure. Not right now. Okay. No. The only fatigue failure would be the gears, and we haven't had a problem with those yet either.
How do you want to test the gear fatigue life cycle?
Just by running it, maybe spinning it a bunch of times. Okay. We just built that prototype that you saw there Friday, so or Thursday or Friday. So we haven't had a lot of time to do like the gear fatigue testing and all that.
All right, then you have to figure out a lot of good stuff. Thank you.
Yeah. Yep.
Okay. Thank you very much, team. Excellent job. Great. So moving on to Group 4, Rolling Universal. This group is unique. We have a singular person in this group. Chris is an EGM student, so and he'll explain his project, but just kind of setting the stage why you only see one person presenting now. Okay, go ahead, Chris. Yep.
Good afternoon. My name is Christopher Rabarchuk, and I was responsible for all aspects of Rolling Universal, which was the development of a universal rolling door end lock. Little background, the rolling door, what is a rolling door? A rolling door is defined as any vertical acting door consisting of interlaced slats that rolls up around a barrel positioned over the opening. You can see here, there's individual slats that are slid together in a lateral direction that then raise vertically to coil up in the coil area, as you can see. What is an end lock? An end lock is a component of a rolling door that assists in preventing lateral movement of the slats that are interlaced together. You can see here are 3 examples of what's used in the market today and how they attach to the end of the slat using rivets. Here is what we're actually going to be talking about. These are the design iterations I came up with for the universal rolling end lock. On the left here is the original that I had 3D printed and used to do my fit testing. The center is the second iteration of a metal version that's going to be steel and stainless steel. And here on the right is the probably the most important, which is the injection molded plastic version that's currently still in development. What's the problem and why are we even working on this? One of the main issues is that each manufacturer uses their own style. There's many door manufacturers and they all basically make the same thing. If you didn't look at them, if you didn't have a trained eye, you wouldn't be able to really distinguish them between one another. Technicians and companies in the field, though, wind up servicing all types, so they need to carry multiple components. If you were able to develop a universal one, you'd be able to only carry one component and make repair much easier. The bigger issue that I've discovered is that the current ones used in the industry lead to slack cracking. As you can see here on the right, here's two examples of what happens over time from the end lock itself and how it causes damage to the slack. It hasn't been a problem in the past because of limited warranty and life cycle. So in the past, these doors weren't expected to do much. They were all generally industrial purposes. They weren't really put anywhere that people use them often, maybe once a day. And they didn't have, much of a long warranty. But now with the demand for a faster and quieter and longer lasting door, this is a problem that's kind of rearing its head in the industry. I did find a solution though, so that's the good news. My theory is that the profile of the end lock is the problem, and that the profile being larger than the slat causes forces being pressed onto the end lock, transferred to the slat, and eventually leads to the slat tearing or cracking, as you saw in the previous photos. The idea would be to develop lower profile end locks to reduce these forces and fix the problem. And if designed properly, the end lock would hopefully be able to be universally mounted across different door types and manufacturers. For the design requirements, the main goal was to improve the profile. This would eliminate slack cracking. As you can see here, the profile in red is of a current end lock being used, and you can see how much larger it is than the actual slat profile. The new profile should improve functionality and durability, and the profile should be designed in such a way to allow it to be manufactured in multiple types of materials, including steel and stainless steel and injection molded plastic. The universal mounting requirement, it should be able to allow it to universally mount and be mounted across multiple door types. I will be looking to make this across a single manufacturer, but hopefully it could be adapted to be used across multiple manufacturers as well, considering how similar all of the slat types are. And here's just an example from one manufacturer. On the right is a drawing of how the insulated version of their door is laid out, and on the left is a drawing of how their non-insulated is laid out. You can see they're pretty similar, but just different enough that to date they've had to use two different components to retain the slats. Specifications. The universal mounting, generally in the industry, everybody uses a rivet to hold the end lock onto the end of the slat, as I showed you in one of the earlier photos. The problem is that the rivet patterns are different on the different slats. So there's two different angles to deal with this. One was create a hole pattern on the slats that's identical. This seems obvious, but it does require a lot of capital upfront, considering the slat sizes are slightly different. They're on different roll formers, so you'd be investing a lot in tooling, upwards of $250,000 or more, as well as any change to slat profile or hole locations generally would lead to more testing for third parties that you have approvals in as well. The second was creating an end lock that has multiple hole patterns. And this is the route that I'm actually going on. The issue with that is there's not a whole lot of room to put multiple hole patterns, so it becomes a little complicated when you're trying to space everything out. Improvements to design. Again, the initial investigations, there were coiling characteristics and slat damage that resulted from the end lock profile being greater than the slat. The solution would be simply to decrease the profile. The one issue with that is that the original design intent of the current end locks, the profile is larger than the slat to reduce wear on the end of the slat and to reduce noise. So throughout testing, we're going to have to see if the new end locks have that effect, if there is a net negative effect from the new end locks, or if other changes in components between finish and things like that have reduced wear anyway, and that's no longer required. Most of the end locks in the field now were developed well over 50 years ago, and they're still in use today because they haven't needed to be changed. The test requirements, I've laid out these requirements to meet prior to this end lock being able to be put in the field. Cycle testing, a minimum of 3 full-scale cycle tests need to be completed for each slat type that's intended on. So that would be 3 full-size insulated, 3 full-size non-insulated units. We put variations in there with material type and speed and things to add variables that we need to test along the way. The size of the units would be determined by market research. Pass-fail criteria would be determined based off of a baseline test that's going to be performed first. The main criteria are going to be slat fatigue, coiling characteristics, and end lock damage over the course of the number of cycles. And to define a cycle, that would be the door going from completely open to closed and then back to open. The physical specifications, this is just really laying out the materials that are used in the industry today. All design profiles that I come up with they're going to have to be able to be made out of steel, stainless steel, and injection molded plastic. And here's the budget. All the budget concerns for this project are being covered by the company I work for, Cornell Cookson. This is being developed for their product line. So as you could see, a basic breakdown. 3D printed prototypes were first, followed by steel prototypes, small scale test apparatus. We'll go over this in just a minute. This is probably one of the most significant cost savings of the project cost itself. As you could see, the total cost of this small scale apparatus is under $500. This is really key to getting quick results and honestly failing quickly. Allowing development to happen fast rather than waiting for the long results that happen from a full-scale test, as well as the cost. Again, this is under $500, and as you'll see on the next slide, one beta test for a full-scale costs almost $1,500. So the cost savings was pretty significant from setting that up. One thing not included here is the hard tooling cost. Those are still being quoted and worked on, so those will be added at a later date. Here's just the basic work breakdown structure. Everything in yellow is something that is started, and everything in green is something that has already been completed. All of the beta testing in this row is going to be handled in the second semester next spring. The initial testing, again, I set up a small scale test. The initial one was made out of unistrut frame and pneumatic pistons with solenoids and a PLC to kind of run everything and simulate the impact from coiling. You'll see in the next slide photos and videos of that. That has since been changed out with a flat steel plate frame to give it a little more rigidity and I think to duplicate field results better. Here's a photo of the unistrut frame. Here's a short video of it operating. You can see the pistons coming down and they impact the end lock to simulate the coiling characteristics of what happened. And then here is the steel frame that replaced the unistrut frame. This was bent in-house to create a little more rigid surface for these pistons to mount to. And then the fit testing that I had said before, this profile was originally created to just do a fit test and see what the low profile ear, which is this region here, looked like on both slat types that I'm trying to capture. That was done without issue. So then I moved on to developing the further steel profiles. Key accomplishments this semester: I completed baseline testing with the small scale test to determine a point at which the new end locks would have to pass. It also helped to establish a comparison between the small scale and a real life test. Essentially, this makes, it validates the small scale a little more. If a real life test failed at 10,000 cycles per se, and the small scale tested at 30, failed at 30, I would know that there's a 3-to-1 comparison ratio. So if I was trying to attain 50 with the new end lock, I would have to meet 150 on the small scale test. I began small scale testing the prototypes after the baseline. That's in progress right now. Here's a modeled version of the next version of the end lock, which is the more universal style. You can see the overlapping rivet hole pattern here, and the double ears. That would help, go on multiple slat types. And then I also began working with a vendor to start working on the injection molded piece. I didn't have a whole lot of experience with injection molding, so it definitely helped consulting somebody with a lot of experience to help develop, some of the intricacies of this profile, such as the raised emboss here and the cavities in the ears to keep all of the thicknesses uniform to help in the injection molding process. What's next? I'm going to complete the development of the end-lock versions, begin and complete full skies beta testing next semester, develop a launch plan. That'll be done concurrently with the beta test, and launch the new end-locks into a complete product line. With that, I'm all finished up. Does anybody have any questions?
I do. This is Dr. Razavi. How are you? It's a wonderful design. Congratulations. I have a few questions for you. End-lock failure, current end-lock failure. I don't see the connections between end-lock failure mechanism and then low-profile design. I can understand. What did you recognize in end-lock failure, current one, and then you decided to go to low-profile design of the end lock to avoid the failure?
So originally this whole project was started. I was assigned a project at my job for making one of our units go 1 million cycles without issue using current components. And my initial tests that I had set up, I was seeing failures in every one, and all of the failures in the end of the slat happened to be around the attachment point where the end locks held on. And then in looking at the profile of a coiled curtain, you could see that as it coils, that end lock profile stacks on the slat below it. Mm-hmm. So as the weight of the door pulls down, you get a pressure point from the profile of the end lock that pushes up.
Can you bring that slide in your presentation? Share it with us when you see the end lock failure happens around the corner.
Sure.
That you see the fracture that you showed.
Yep. Let me.
I believe that it was initial slides. Yeah, this is it. Yeah.
This here?
Yeah. Then what you see here is these are the fatigue failure, right?
Correct.
And then based on what was the load there? What was the was it combined loading, or you think that was a just single loading, or it was a shear or combination? What do you think is happening here?
Really, I kind of attribute it to fatigue over time. So as these coil, it's kind of unique the way that the slats would crack. is it would always start near the top of the curtain. And then as more cycles were added, you would see more cracks further down the curtain as time went on.
Yep.
So what I attributed that to was the initial coils wrap up and have that stacked, and more weight actually gets added to that on top as it coils up. So it causes the initial, the top portion of the curtain to have more force being pressed down and causing that bending moment on the end of the slat. So it just takes more time for the lower ones that have less weight on top of them. So that's why they took a little longer.
It's advisable that you show the whole thing in terms of the connection to door, how this load is transmitted to your end lock.
Okay.
The other question I have is, okay, based on what you are saying, and I don't see the whole picture yet, is you change the whole design to low profile. What is the advantages of your design, as you call it, low profile, that would avoid the fatigue failure in that part?
So if you look at my screen here, this red profile being larger than the slat, right now I decrease the profile to be smaller than the slat profile itself. So as the door coils, all you're getting is the slat laying on top of another slat. So there's no actual bending force or anything attributed. It's just a flat surface laying on a flat surface at this point. That's what I mean by the lower profile.
Oh, lower profile means that your force distribution does not cause any bending.
It essentially eliminates the force distribution that I'm seeing. It turns it to zero.
It's a very good idea. It's an excellent project. It's a good idea to have extra slides to connect these things to design together, that for the people that they see your presentation, those connections becomes important, because I didn't understand the low profile design. I didn't understand the end lock failure. And then I'm sure it's a wonderful sort of the transition, and you're finding the good design by low profile, but it is not clear how did you move on to low profile. I suggest that you add up perhaps a slide to explain the connectivity of this stuff for door in terms of the load transmission, and explain the failure mechanism of end lock, and then your decision to go to low profile.
Okay, thank you. Thank you for the feedback.
No problem.
Okay, so we're running slightly behind schedule, but that's okay. Great comments, great feedback from our faculty. So we're at the point in our schedule where I have quick break. Let's make the break as quick as possible. Maybe just 2 minutes if you need to grab a drink or stretch or whatever, and then we'll start right back up in just 2 minutes. So thank you, Chris, and quick break coming up.
Chris, are you still there?
Okay, everybody. So I'm going to try to keep us or get us slightly back on schedule if I can. So we're going to move on to Group 5 King Lift if you guys are ready.
Yep, just one second here. There we go. All right, I'm ready whenever. Should I start?
Yeah, go ahead.
Hello, everyone. I'm Ryan Cup.
Saad Al-Joid. Dramal Qaidis.
Faisal Shamari. And our advisor for this project is Dr. Rizavi. And this is our King Lift final design presentation for ME391 Group 5. So an overview of what we're going to cover here is the background of the King Lift system. We'll go over the requirements of the system. We'll talk about the specifications in terms of how we plan on building it, the design and components that make up the King Lift. We'll go over the testing, objectives, and methods. We'll go over the budget and price of the product. And then finally, we'll talk about the work breakdown and our current progress.
The background of our project: the King Lift is a four-wheel, four-vehicle wheel dolly, accurately and precisely repositioned and powered vehicles, retraction by actual lift vehicle. Our design for the King Lift inspired by GoJack, which is a top market product. The wheel dollies on the market are nearly unusable on cracked, sloped, or uneven surfaces, and our objective is to provide wheel dolly for use on average driveway, garage surfaces. And we intend for mid-size sedans, and this negates the need for smooth driveway or coated garage surfaces. Requirements: frame and wheels. The dollies lift vehicle by the wheels with retraction force, and the strength of the frame should be support up to 3,800 pounds to 4,000 pounds. Mid-size sedans typically weigh up to 4,000 pounds. The wheel dolly arm should be able to withstand repeated lifting and extend during operation. The wheel should rotate and have a good alignment and roll over cracks and gap at the surface. They should also be able to withstand load and pressure. Actuator and suspension. Actuators needs to be operable by user and safe operate. Actuators need to provide force necessary to lift and support vehicle. Suspension system to better protect against system collapse. Damping system to prevent free rolling.
Next, we have the specifications of the system. So the wheel dolly is made of a 6061 aluminum frame that extends and retracts. It's got a 4140 steel tube lifting arms, as seen here, these cylinder tubes. The wheels are made of neoprene hard rubber, and they're treaded, and they are placed on McMaster Carr's threaded stem swivel casters. The actuating component is the compact hydraulic cylinder, and this is what extends and retracts the frame. An alternative to that is a purely mechanical linear ratchet pull system that's built into the aluminum frame, and this eliminates the need for a hydraulic cylinder. And finally, a kick pedal is what allows the actuator to be operated. So here's the design assembly here. Here's the drawing of the frame assembly here. We have an inner and outer frame made of aluminum. We've got the two steel loading arm tubes. We have 4 casters per dolly with 360 degrees of swivel each. And then there's an actuator component that extends and retracts the frame. And at full retraction, this should be at most 12 inches, and full extension should be at least 24 inches. And this just allows the dolly to grip smaller and larger wheels. And the max height of the dolly should be 5 inches, just so it can fit under most vehicles. And ours is currently at a height of 4.83 inches.
first part of the component is the frame, which consists of the inner and outer frames. Both of them are made of 6061 aluminum with rectangular tubes welded to shaped lift arms bases. On the other hand, lift arm tubes are made of 4140 steel cylinder tube with 13 tapped holes for threaded steam caster mounts. All 13 holes have half inches diameter.
Next, we're going to look at the actuator here. This is the McMaster Car Compact Hydraulic Cylinder product that we plan to purchase for the prototype. This is a 1.5-inch bore, 3-inch stroke length cylinder. And here's a drawing of it here. And the reason we're going for this compact cylinder is to fit within the size constraints of the wheel dolly. For a mid-size sedan wheel dolly, we don't want it to be too big, else the hydraulic cylinder will retract too wide and extend too wide for a mid-size sedan wheel size. The alternative to the hydraulic cylinder is the linear ratchet pawl frame, which is built into the aluminum frame itself. And this is an example here from the GoJack system. It's just like a stepladder system with a ratchet pawl that locks the retraction and extension in place of the frame system.
The last part of the components are the caster wheels, which are made of Neperon hard rubber. By replacing nylon with the Neperon hard rubber, it will make the wheels able to perform under heavy duty for easy travel of common surface. The wheels will have total height of 5.18 inches, include threaded steel.
Next, we're going to cover the testing of the King Lift. Here's the objectives. First, the dolly has to support vehicles of up to 4,000 pounds in sets of 4, meaning 4 dollies need to support 4,000 pounds together. These need to also withstand repeated loads for extended periods. And the dollies need to remain stable under unstable loading conditions, for example, rocking, shaking, and uneven weight distributions on the vehicles. The rolling needs to be smooth with various loads. The rolling needs to be smooth over unsmooth, cracked, and otherwise imperfect surfaces. And here's an example here of how the King Lift lifts the tire. It's got the 2 lift arms here, and here's the big tire in the middle. And finally, we plan to determine the safety factor of the King Lift system through our testing.
For testing specification, each dolly has 2 lifting arms and 4 casters. Dollies must withstand repeated and extended duration loading. One dolly supports one corner of the vehicle. Typically, mid-sized sedans weigh up to 4,000 pounds, which means that each dolly must be able to lift 1,000 pounds. To test dolly ability of lifting the requirement load, we will apply the load and make sure that the dolly will stand over a long period of time.
Next, we're going to cover our methods of testing. We have various methods here, and the first method is with 2-arm testing. In this case, we'll place 2 load arms parallel and suspended by supports on each end. And then we'll place a large load, such as a tire, on the center of the arms, such that the tire is supported by both arms at the same time. As seen in this picture, here's 2 load arms supporting 1 tire. And in this case, we plan to vary the load magnitude, the distance between load arms, and the duration of loading. And in varying the distance between the load arms, we can see that the location at which the tire will contact the lift arms will change, and so will this angle of force here, as seen in the red arrows. For this test to be successful, the load arms should support a combined load of 1,200 pounds or more for an extended period with no deformation or failure. Our second method is the single load arm, and in this case, we're going to be testing the load angle rather than the load arm distance. So in this case, a single arm is suspended by supports on either end. The load is placed on the center of the arm. Rotate the arm and repeat loading for various rotations. As seen in the picture here, we're going to rotate the arm and just place the load on the center again and again and again. And in this case, we're going to vary the load magnitude, the load angle, and duration of loading. And in varying the load angle, it's similar to the distance between the 2 arms. The location of contact between the load arm and the tire will change with this angle, and so we need to test that as well. And success depends upon the load arm supporting up to 1,200 pounds, dependent on the load angle with no plastic deformation or failure.
And here I'm going to talk about our budget and price for our project. This list shows the part that needed for our project to be achieved. We have 3 different options of the total cost. So if we use a new materials, that cost will be $621 as a first option, means that the cost will be over budget. The second option for us would be $414 if we use aluminum and steel from the machine shop. That means the cost will be under budget. Our third option would be $160 if we use a basic mechanical design instead of ready-made cylinder plus the aluminum and steel that we will have from the machine shop. And this way we will save hundreds of dollars. And here's our work breakdown structure, and I'm going to talk about it more on the next slide. Here's our schedule and our Gantt chart based on the WBS. And we have 6 main aspects. And we already covered the first 3 for the first half, which are the project management and planning. And we are finishing the component design. And we are ahead by a couple weeks. And we are currently focused on procurement and assembly, considering options for component sourcing. And here is our second half of the project. Focuses on testing and simulation, and we have a total progress at about 45%.
Okay, so in summary, that was our King Lift wheel dolly system. We went over the background, its purpose, and the problem we were trying to solve. We went over the requirements that the dolly had to meet, the specifications in terms of how we planned on building it, what requirements it had to meet, the design and components that went into the system. We went over our testing objectives and our testing methods that we plan to use. And then we covered our budget and our price for the product. And then finally, we went over our work breakdown, and then we covered our current progress. Thank you.
Okay, thank you guys. So we have a couple minutes for questions.
All right, I'll go first. Okay, so you guys didn't mention anything about like valves or pumps or oil reservoir. Like, where does the power source come from? The hydraulic power, where does it come from?
Right, that's one of the considerations we had to think of, because we're not focusing on that aspect, which is why we were considering the mechanical.
Then why would you need a hydraulic cylinder?
Right, that's what we're getting at here, is that we were going to use the hydraulic cylinder from McMaster Carr with the hydraulic the fluid pump itself, but since that's not the main focus of our system, and because the hydraulic cylinder is so expensive, a ratchet pull mechanism, which is just purely mechanical like step ladder system with the ratchet pull to lock the extension and retraction would be a possible alternative, which would be built into the frame itself.
So essentially what you're saying is that this is more about the mechanical design, less about the testing and hydraulic system.
Right, the hydraulic cylinder is what we wanted to do because there's pros and cons to the hydraulic cylinder and to the ratchet pull system. Like the hydraulic cylinder would be safer in our opinion, and it would provide more force, but at the same time, it needs that fluid, which a ratchet pull system doesn't need. So rather than think about the hydraulic cylinder itself, because that wasn't the main focus, our main focus was just to make sure that the wheel dolly can roll over common driveway and garage surfaces, purely in the design of the caster and the wheel, rather than focusing on that cylinder. We just decided if we aren't going to use the hydraulic cylinder with the fluid system, we will just design a ratchet pull system into the aluminum frame.
Okay, that's a good point. So which means that you pretty much don't have to mention anything about the hydraulic system because you're not using it anyway, right?
Yeah, it's just that's just one of the cost options, technically, I guess. It's not the main focus of our design. So,
but I think moving forward, you really don't have, because that's not going to be part of your design anyway. It's really, you should focus on your own design. I mean, just otherwise, because think about this, the practically that's not going to be possible either. I mean, not everybody can afford a hydraulic system in their garage, right? So.
Right.
Okay, I'm going to cut off questions so we could somewhat get back on schedule. But thank you very much, guys. Virtual clap.
Thank you.
From me. And then, so we're going to move on to the next group. We're on to group 6, EZT. And while they're loading up, just a reminder to all the other groups to please upload your PowerPoints, Senior Projects 2 as well, so I can have all the, oh, I love the custom backgrounds. That's great. You guys planned this out well. They got their logo in their backgrounds. You can identify their team. That's a good idea. I should ask to do that every year. Okay, go ahead, guys. I don't hear your volume. Don't forget to share sound bottom left.
Is a mechanically self-loading baseball tee. Hi everyone, this is the Easy Tee. My name is Bryce Snyder.
I'm Colin Dominic.
I'm Joe Kaczynski.
And I'm Jonah Harder.
And our advisor is Dr. Gamari. And our project is a mechanically self-loading baseball tee. Here's the Easy Tee final design. We have an assembly down here that's going to be the tee and the shell assembly. And then we have another one over here that's the track assembly. So basically balls are going to be loaded on here. They're going to flow down towards the tee assembly through this hole in the shell. Basically, somebody's going to put their foot on this foot pedal here. It's going to bring this down and this inner tee assembly down. From here, a ball will load on to that tee. And once the foot pedal is released by taking the foot off of it, come back up, bring that back up, and a ball will be here ready to hit.
This is the Easy Tee background and problem statement. Unless you have two people while using a baseball tee, the process is often slow. If one person is only using the baseball tee, it requires them to break their stance to pick up another ball. The baseball tees that are electric, it often needs power sources. They're not portable because they're very heavy. So how do you make a baseball tee that requires no power, but it's still easy to use for one person? And at the bottom on the left, it's just a traditional baseball tee. And on the right, it is an electric baseball tee that requires power and is heavy. This is the Easy Tee introduction. What we did, we came up with a mechanically powered baseball tee that requires no electric power. It reloads the ball with a step of a foot pedal with a spring mass damper system. It can store up to 20 balls on the track at a time, and it's lightweight, weighing in at about 16.3 pounds.
Here are the requirements for the Easy Tee. First, touching on the materials, the Easy Tee includes both dynamic and static parts. So for the static parts, we need materials that will be able to keep their shape as the dynamic parts are moving. And with the dynamic parts, we need them to keep their shape as they move up and down. And both of these also need to be lightweight so we can implement the portability. And for the baseball part, we need a material to be able to hold the baseball and be able to absorb a high impact force, the swing of the bat, for many cycles so it doesn't break on the user. So for the dimensions of the Easy Tee, we needed the outer shell and track big enough to be able to hold the baseballs and allow for movement. And for the tripods, we needed them to be long and thick enough at the base to support the main assembly, and the bipod for the track to be able to support that as well. And then overall, we need the weight of all the materials to be light enough so it can be disassembled and transported easily. So the specifications for the Easy Tee, as I mentioned before, we decided on PVC, aluminum 6061, and neoprene rubber. The PVC is the outer shell and the track and the tripod and bipod. The aluminum 61 is the inner tee assembly along with the foot pedal. And the neoprene rubber is the tee topper, which holds the ball. And the main dimensions and properties I want to hit on is from the ground to the top of the tee is 36 inches. This is the lower end of a standard baseball tee. For the track, it's 5 feet long at a 15-degree angle. We wanted to be long enough to hold 20 balls. For the pedal, it's 16 inches off the ground, which doesn't require too much movement for the batter to be able to activate it. And for the springs, they are 2.906 pounds per inch, which moving the pedal up and down, it requires a force of 56 pounds, which isn't that much considering the batter is stepping down on it. And the total weight the Easy Tee came out to was 16.3 pounds.
Here we have the flow diagram of how the tee works. It starts by pressing the pedal to extend the springs 16.5 inches to then lower the middle of the tee 10 inches. When the foot pedal is released, the ball is raised to 36 inches above the ground for the player to hit it. Our budget is outlined here, showing the cost per model in yellow of $379.89. Our Wilks price is in green of $494.50. Here is our work breakdown schedule. Outlining some important parts here, we have defining our core problems, identifying our project scope, acquiring our parts, test in a computer simulation, and deliver papers.
Here we have the schedule. We have project proposal, design a project, and fall report being covered in this fall semester. Project proposal is basically just listing everything that Dr. Bednar's wanted us to hit on in the syllabus. We have like the roster, description, specifications, requirements, and all that. Then we have design a project. We have alpha design. That was our first design, which was revised into the beta design when we met with Dr. Gumari. The fall report is this report today. Then we have ordering. Ordering has already begun, and we have received some of our parts. So basically, building and testing is our next phase, and we are planning on starting that today and having it be finished by March 16th. That date may change, may not, not exactly sure yet. It all depends on how we go about manufacturing parts over this winter break.
Now on to our design. Here we have a shell subassembly. As you can see, there is a PVC tripod attached to a PVC shell. They are attached via aluminum U-channel. The shell has a hole cut near the top to allow balls to roll in and a slit cut near the bottom for the foot pedal to go in. This is the T subassembly. There is a foot pedal and support attached to a metal upright. This upright is welded to a bottom that will have a spring connected to it. There is a groove machined into this bottom where an O-ring will be placed as a damper. The springs reach up to part 1, which is stationary. The T-topper is attached to the top of the metal upright and is made of rubber. This is the track subassembly. It consists of a PVC bipod and a PVC track. The bipod is again attached with a U-channel. There is a track connector at one end that will slip around the shell and be bolted into place, allowing balls to seamlessly go into the T. Here you can see it all put together. As you can see, the T subassembly goes inside the shell. Nearly everything is bolted and nutted together.
This is our testing plan. It consists of computer simulations, physical testing, and real-world testing. Under computer simulations, it models the outcome of the physical system and shows possible weak points using Inventor. Physical testing is test the prototype for qualitative and quantitative results, including fatigue testing, stress concentrations, dampening of the system, making sure the springs do not throw the ball in the air once the foot pedal is released, and static equilibrium, meaning the T doesn't fall over when standing and or the baseball sits at the correct height. And the real world testing determines to what extent complete misuse of the system can survive.
Begin the computer simulations. Here we have the full assembly undergoing a force from a baseball bat swing under normal use. This is showing displacement of the system. The baseball bat is exerting a force of around 3,400 newtons or 764 pound forces. I believe that the T-topper is the only part moving here because it's made out of rubber. As you can see, the rest of the system is blue, meaning that is unaffected from the swing. Here we have the full assembly for von Mises stress, basically the same force being applied in constraints. Von Mises stress is a value used to determine the yield failure criteria of materials of the system. So as you can see here, everything is blue, meaning that the system is pretty much being unaffected and nowhere near yield points for the materials. I believe that that's because this part here that is moving is rubber, the T-topper. That's just going to soak up all the force of the baseball bat swing.
This is the displacement of the shell as if it was hit by a miscalculated swing. The force of the baseball bat is 760 pound force, and the constraints are at the arrows there you can see, and that is where the tripod legs connect to the shell. In a real world situation, when you hit the T with the bat, it'll more than likely just tip over, but for computer simulations, we could find out that the shell will displace around a ½ inch. And this is the von Mises stress of the shell again, when it's hit by a miscalculated swing, same constraints and force. And you can see that the constrainted areas have the highest stress, but still nowhere near the yielding stress of the material. This is the principal stress on the shell, as if it was hit by a miscalculated swing. Principal stress is the maximum and minimum normal stresses on a particular plane, where shear stress is 0. So again, you can see that the constrainted areas of where the tripod legs will fit into the shell are the areas of the highest stress, but again, the material will be safe from yielding.
So now on to the computer simulations of the EZT undergoing the foot pedal load. So as you can see, the force is 56.38 pounds, and this is the total displacement of the T as it undergoes that force. So the maximum displacement of the system is only 0.02 of an inch, which is very good for this system. And most of the displacement is at the bottom of the T. so that's not too much of a concern for us. The only main concerns are the displacement of the legs of the tripod, because that is what is supporting this assembly. This graph shows the von Mises stress on the assembly, and as we saw before, there's not much of a impact on the system as a whole, because none of the stresses in this system are close to their yield stress. And then here's the principal stress. Again, there's not much to see here. This just shows a negative 1.12 KSI stress, which is not much considering the yield stress of the entire system.
Here's physical testing. So we're going to do stress concentrations. We're going to apply strain gauges to areas of presumed high strain, most likely around the welding of the foot pedal to the T and to the T to the bottom of the T. Just want to make sure that it's going to be able to withstand the force of the pedal being pressed. Here we got damping of the system. We're going to lower the springs, allow them to return to their origin. We want to make sure that the damping is not overdamped or underdamped. Overdamping would cause the T to not return to its origin, and underdamping would cause for the T to return too quickly, causing it to move the ball off the T before the batter can swing. We also want to make sure that when the T returns, the damping is going to allow it to sit in equilibrium and not oscillate. Static equilibrium, we're just going to put the assembly together and make sure that it doesn't move when it's not in use.
So for the real world testing of our system, we want to test the misuse that could happen with baseball players using this. The main thing is hitting the tee at the shell instead of at the tee topper. So what we're thinking is it's going to knock over the tee. So what we can do is we're going to take the tee and hit it with a bat at the shell and see what happens. If it gets knocked over, is it going to break, or are there any potential weak points that we need to reinforce? Also, the bending of the legs, as I mentioned earlier, is something we need to think about, as over time, the bending can become too much and we don't want the PVC pipe to plastically deform. And then some extra tests we can run is exposing the tee to rough weather conditions.
As of right now, we have begun the ordering process and received some of our parts, but looking forward to next semester, we will begin machining and assembling these parts. We will do some real world and physical testing and analyze these results, determine what can be approved if anything goes wrong with it, and we will fix it. And then we'll test the revised design, and then we shall repeat this until we're satisfied or the end of the semester.
We'd like to acknowledge some people. We have Dr. Gamari as our advisor, Dr. Bednarz as the professor to this class, Dr. Mu is 3D printing the track connector for us. Lisa has been helping ordering and receive the parts, and Adams has been helping the inventory of the shop, and he's going to also help. Here are our references. And does anybody have any questions? Hi everyone. This is the EasyT.
Okay, thank you guys. So we have a couple minutes for some questions.
Ed, this is Tim. This is Razavi. You mentioned in your presentation there is an O-ring that acts like a damper in your mechanical machine design. How do you select the O-ring that is going to be underdamped or overdamped in your system?
So basically, when we went and ordered this O-ring, we are just kind of under the presumption that the inside of the shell is at a diameter of, I believe, 4 1/16, and the bottom of the shell is at 4 inch. So we ordered a O-ring that would be big enough to cover from 4 inch to, it'd be basically 16th inch thick or bigger. We did not do any calculations to determine if this is going to be a correct damping or not. We're just basically going to build the system and determine then once we put it together by moving it up and down.
Therefore, you don't know the amplitude of the stress that is being applied to the O-ring, and then it would be sufficient in terms of the material thickness that is going to damp your machine design.
Yeah, basically.
Okay.
For now.
One more suggestion for you. When you talk about the dynamic system like this, it is a good idea to clear your presentation, have mechanical powered components to be identified, because this is a complex system. It's a wonderful project, but for the next time, it's good idea to show the essence of your project, which is mechanical powered system component. Thank you.
Thank you.
Okay, I have a question. Okay, you guys said that it looks like your main concern is if all the mechanical, looks like you have a pretty good chance to get all the mechanical components to work together, right? So that's, I think that's a relatively lower risk, but it seems like you're mainly worrying about like if the bat hits a T, right?
Yes.
Okay. So,
and the damping of the system, yes.
okay, so if that's the case, the T is made of PVC, and do you think if that happens, would the bat actually, would you worry about more about the bat or actually more about the T? Like that's what I'm trying to understand.
Well, when we say about the bat hitting the PVC, the T topper is about 5 inches above the actual shell. So for someone to hit it down there, it would have to be a very miscalculated swing. It's more of a worst case scenario than something we expect to happen a lot.
Okay, but you still decided to do that test.
Yeah, we're just trying
to cover all of our bases.
Exactly.
And you think if that happens, you worry more about the T, you worry less about the bat?
Yeah, the bats are usually made out of aluminum, so I believe that it should be okay.
Okay.
Okay, thank you very much, guys. Virtual clap. Usually you get thunderous applause in Stark 101, so we'll try to do this the best we can. Yeah, great job, and a great job again on that virtual background. That's, I'm going to recommend that to future teams. I like that. All right, so you're welcome. All right, so we're moving on to Group 7, Path Cedar.
Our project is a path seeder. The group members include Jay Patel, Mike Ellis, Matthew Angara, and Matthew Driscoll. So tending to a home garden seems like an easy task, but over time can prove to be physically demanding. The tasks involve having to bend over, dig up the dirt, and place the seeds, which causes strain to the gardener's hands, knees, and back. There are already products created to aid in the act of seeding, such as crop seeders that are used on farms. However, crop seeders are used for large-scale seeding instead of smaller home gardens. So this project intends to create an automated seeder that will remove the risk of injury and allow the user to relax while the garden is being seeded. Each function of the path seeder will be tested to gauge the functionality of each part, and as a result of the test, adjustments can be made to the parts list when needed.
Our project has several key components that will need to be tested. Those include the wheels, the digging method, the seeding method, the covering up method, and the communication between the beacons and the smartphone/computer. All these are very crucial in making any adjustments that will need to be made for the project.
So one of the key components is the base of the system, which includes just a set of wheels on and held by a platform, which will hold the rest of the components on top. In order to test the wheels, we have first. Sorry, that was a wrong file apparently.
Yeah, that was the one we made for the 384 class. Sorry about that.
It looked familiar. I was going to say something. I thought you had a similar intro. All right. You got the right one this time?
Should be good. This is Matt Driscoll and myself, Jay Patel. Our group advisor for this project was Mr. Griner. This is the final design of our overall path seeder. As shown on the left side of the screen, this is an isometric view of the system. Along with this, on the right side, it shows the side view of the path seeder. The way path seeder will work is it will constantly dig a little trench as the system moves forward with the use of the 2 stakes that are placed almost right behind the front 2 wheels. Then the seeding mechanism will drop the seeds as instructed by the user, followed by the end of the system, which will cover the seeds along with the soil that has been dug up.
Tending to a home garden seems like an easy task, but over time can prove to be physically demanding. Having to bend over, dig up the dirt, and place the seeds causes strain to the gardener's hands, knees, and back. This can potentially lead to serious injuries, especially for those with pre-existing hand, knees, and back problems. There are already products created to aid in the act of seeding, such as crop seeders that are used on farms. However, crop seeders are used for large-scale seeding instead of smaller home gardens. This project intends to create an automated seeder that will remove the risk of injury and allow the user to relax while their garden is being seeded. As of right now, there are no automated seeders that exist on the market. The basic requirements the machine should meet is to dig up a trench, drop seeds into the trench, cover the seeds with dirt, and follow a user-defined path. The path seeder should also be able to communicate with a smartphone/computer via Bluetooth, as well as communicate with the beacons to know its precise location. Then, for movement requirements, the path seeder should move forward using its two back wheels and turn using the front two.
The path seeder is going to have two sources of power. Firstly, a single 20-volt battery, as well as a set of AA's, which will provide 6 volts of power. To drive the seeder, we'll have two motors, two 24-volt DC motors, which will be run at 20 volts. One of these motors will drive the back wheels, and the other will provide steering at the front wheels. The seeder must dig a trench for the seeds to fall into. It will use the stakes and the shovel. Using the servo and a custom-made attachment to the servo, the seeder will drop the seeds into the trench. And then, using a garden hoe, the seeder will cover the trench back up with soil. Using the Arduino microcontroller, as well as the HC06 Bluetooth, the seeder will wirelessly communicate with the user's phone or computer that they will use to draw a path. The seeder will have a router on top of it that will communicate with the 6 beacons in order to pinpoint its location within centimeters of error. This is the budget. It shows how much this design will cost. We have 2 categories here. The far right one is the prototype price, which is how much it would theoretically cost if we made this all from scratch. This comes out to over $1,000. Fortunately, we've managed to acquire many of these items in-house. For example, the first item, the beacons, our highest cost item. We were able to acquire from one of last year's senior project designs. This, as well as a lot of existing parts, has made our project cost come down to about half of our $500 budget.
Shown here is the work breakdown structure. It is broken up into 4 main sections: the design, project management, external, and build. This goes along with the schedule, which will be explained in detail on the next 2 slides. This is the schedule shown for the first semester. As you can see, this semester was mainly about finalizing the design and the project management side of our project. We are on schedule for the first semester as we completed the requirements, specifications, as well as finalized our design. Along with finalizing our design, our budget and planning was finished also to ensure our group is ready to order parts and build our prototype for next semester. Leading into next semester, we will begin constructing the prototype of our project. We plan on ordering all parts and begin testing the important components of our design. We also begin writing the code in order to communicate between the Arduino, beacon, and computer being used to draw the path of the path seeder. The test plan of the path seeder will consist of testing the main components of our design. Those include the wheels, which need to be tested on wet and dry soil to make sure they do not slip or bury themselves into the ground while moving. The motors for the wheels will be tested also to make sure they're powerful enough to get the wheels through any obstacles in their path. The digging method will also be tested, as the spikes and trowel need to be able to dig both wet and dry soil, as well as not get stopped by any rocks or objects in their way. As well as we need to make sure they dig a deep enough trench for the seeds to be planted. The seeding process will be tested to make sure a jam does not occur when the servo motor is isolating the seeds and dropping it into the chute. The covering system needs to make sure that it properly covers the soil back over the seeds dug up from the spikes in the trowel. And lastly, the communication will need to be tested to make sure the Arduino can connect to the Bluetooth module and connect to the smartphone/computer used for drawing the path. The Arduino should also be able to communicate with all the beacons in order to follow the correct path. These tests are important for the construction of the prototype of our project.
This is the base of the path seeder, which is made of the front two wheels and the back two wheels, which then support a flat plate on top, which will hold up the electronic components and the seating mechanism. The way the path seeder is able to move is by using the front two wheels as a directional set of wheels, which will be controlled by a single motor connected to a gear and pinion system. The back two wheels will control the speed of the path seeder by moving them forward and backward. The two motors will be used are 24-volt DC motor, which will be powered to a 20-volt due to the limitations of the H-bridge.
The path seeder will dig the trench in two phases. Firstly, there's going to be two stakes hanging below the base, and they'll be used to soften the soil. Right behind those is going to be the shovel trowel tool that's angled so that it'll dig a slight path in the soil.
This is a seeding mechanism design. The way this is intended to work is the funnel will act as a container for the seeds, which will then drop the seeds into a small cylinder, which will be then connected to a servo motor. The cylinder at the bottom is designed with one hole as shown in the figure. The seeds will drop into the cylinder, and when the user wants to drop the seed, the servo motor will turn the whole cylinder, which will drop the seeds at the same time. It will cover the end of the funnel so more seeds do not drop.
For the covering, at the back of the seeder, we have this free rotating part as shown that was inspired by a gardening hoe. It will catch the dug up dirt and push it back into the trench to cover up the seeds. This part should be able to push the dirt over, whether it be wet, dry, or have rocks.
This is the circuit that will be used to control the path seeder. A Bluetooth module will be used to connect the Arduino Mega so that the files can be transferred via Bluetooth. This way, the user does not need to manually connect a cable in order to upload a new path, and this allows for live updates on the computer as well. A set of beacons will be used so that allows the path seeder to know its precise location and follow the user's path. With the use of an H-bridge, the two motors that will control the directional motion and the speed of the system can be controlled. In order to power the overall system, two power inputs will be used. One will supply the 5 volts for the most of the system to run on, and the 20-volt battery will be used to power the two DC motors.
Moving forward, we will be continuing work for this project over our 2-month break. During that time period, we plan on finalizing the digging system of the path seeder. As of right now, we are using the stakes and trowel, but we also have the option to use saw blades. More work and research will be done on this over the break. Like Mike elaborated when talking about our schedule next semester, we will order all the parts needed to build the prototype and perform tests. As a result of the tests, we will be able to see whether or not the parts meet the requirements of the machine. By the end of the semester, we expect to have finished building the circuitry for the path seeder and the mechanical body.
And in conclusion, the path seeder will function as an automated seeder to aid those who own and tend their own home gardens. The path seeder will make the trouble of having to plant seeds go away by digging, planting, and covering up seeds at any location the customer wants. There are no other automated seeders for home gardens on the market, So this product will help many people. Thank you for listening. And are there any questions?
Okay, thank you guys. All right, so we have time for a couple questions, please.
Can I ask a question?
Yeah,
go on.
Dr. Gamari.
Yeah, okay. One quick question. Is it going to be an autonomous system? Because you mentioned beacons and stuff. Is it going to kind of follow some beacons and go through paths?
So it's going to be mostly autonomous, except for the part when you, at the beginning, a user is going to enter a path for it to follow. And once the user has done that, it's going to fully follow that path and put the seeds where it's indicated, on the path. But after the user has defined the path, that would be the only part that the user would have to do.
Okay, so how many man hours do you plan to put per week for next semester as a group?
Every week, or you mean like per day?
Every week, just as a number.
Yeah.
How many man hours do you think you're going to put? What is the plan?
So, over the break, we're planning. So we already have the beacons over the break and the Arduino. So I want to get the beacons working over the break, the beacons and the Bluetooth. So I'm hoping before the next semester.
What is a number in your? No. I just need a number. How many man hours do you think the group should put per week, so that for 392 you will have a successful prototype? What is a number in your head? Do you think?
10 hours maybe.
Per person?
That would be for the whole
per group?
Yeah.
You are way off. Okay, so I'm going to tell you something. I apologize if I sound a little bit sour or maybe bitter, but you better hear from me right now. Every autonomous project I've seen over the past 4 years, all unsuccessful. All. Because of the biggest scope that people define. And they have some ideas in their mind. I'm going to do this. I'm going to do this awesome thing. And there's a lot of pitfalls down the road. At this point, what you have done is a planning, and you have done a very good planning. You know what you want to do. You seem that you're aware of all of the pitfalls, all of the troubles that you're going to face. That's good. But you haven't even gotten your feet wet. There is no code. You haven't prepared the code, the Arduino, the assembly, the issues. So let me tell you something. If you put less than 100 hours per group, you are not going to be near successful. So, and that's the minimum, I think. 100 hours, which means you have 4 people, right? 25 hours each person. Seriously. Otherwise, it's going to be one of those so many unsuccessful autonomous projects we had. Snow blower, what is that? The lawnmower, snow remover from a car. We had so many of them. They never get to anywhere. You're not going to get close to have something running. If you said that the farmer is going to push the device, I would say, yeah, there is a chance. But making that autonomous and going through all the issues, different type of soil, is going to be dry, is it going to be wet? What if there's a kind of bump on the road? How is it going to kind of turn? Again, I'm sorry if I sound a little bit kind of sour, but you have to either change the scope of the project. This is big. This is big. Okay, I don't expect something like that for 391.
Maybe I have a little bit more.
Either change the scope or be prepared to spend 20, 30 hours. Yeah, sorry, maybe Dr. Zook have a better tone. Okay, just my comment. Your planning is great. If you have like three years from now with 10 hours a week.
All right. Okay. So
in a semester, I'll see 4 months.
Okay, let me echo Dr. Gamari's concern first. That's definitely, you guys definitely, I think from very beginning, I had a conversation with Jay. I said, this is the 3rd time somebody's using this GPS module. The other 2 teams were strong teams and they were never able to get too far. So here's my quick suggestion to you guys. I think you can maintain, everything you designed so far can still work, but you might want to abandon this GPS idea. Instead, you use an XY track, because just some kind of XY frame. So it's kind of like a sensing machine, just control XY position using 2 stepper motors to control your position. Because that's going to really get you away from this whole, at the same time, everything you've done so far can still be useful.
Yeah,
Okay.
I think,
Thank you.
yeah.
No, thank you.
And and that's one of the purposes of having this midterm presentation and getting advice from other faculty members that have seen projects from years and years and years. They'll help you adjust this into the Goldilocks zone. Remember, we talked about first week of this project that you need a project that's not so simple that you could bang out in 2 weeks, but not so complex where, like Dr. Gamari said, it's going to take you 3 years. We need one that you could finish in 2 semesters. And I think, using Dr. Gamari and Dr. Zhu's advice.
And also, you guys mentioned because this is for smaller gardens, right? So that's especially true. If it's small, why do you have to use GPS? You just do an XY frame, just control the position. That's going to be so much easier if it's just small.
Ed, I have a very tiny question.
One quick question. Go ahead.
In the presentation, they said there's a centimeter error. How they find out there's a centimeter error between digging and seeding?
That's the Beacon's online, the Beacon website posted that it's within a couple centimeters of error. So I'm just going off of what the Beacons themselves have specified.
And the other question I have is the depth of the dig communication with the seeder. Is this variable or is it displacement of the dig? How do you communicate between the depth of the dig with your system and the seeding?
The digging's a constant size trench.
Okay.
With the stakes and the trowel type method, that's a constant. It's just a constant trench as long as it's moving along its path.
The displacement of the dig is already planned. It's not variable.
No, it's not. It would be
Yeah, no.
This is related to the previous discussion that you had with the other faculty, and you're right in terms of that would be ideal flat situation.
It would be. It would just be moving on the XY plane. It wouldn't even have a Z involved in it technically. So there would be using the beacons would actually it's like Dr. Gamari and Dr. Zhu said. It would making it more complicated than it needs to be.
Yeah. I agree. So. Thank you, Jay.
All right, thank you guys. Great job on your presentation. Virtual clap. Matt Driscoll, you look like you're in the witness protection program. That's
yeah.
I was gonna say that, yeah, but I don't want to be offensive.
Dr. Zhu thought he was in a dark screen.
Yeah.
Okay. I couldn't help myself. It's getting late on a Saturday. It's getting late on a Saturday, so I had to say something. Okay. Speaking of 5 o'clock somewhere, we're on to the Brew Lab game, which is Group 8. So look how I did that segue, huh? Okay. Spencer, you guys are up. Can't hear your audio, sir. You may have to stop share. Try resharing with audio enabled.
So it says that it's shared. I think that it might be a little quiet. Let's try this again.
Good afternoon. This is the Brew Lab. Our group members are Corbin Schlichter,
Can you hear it?
Dalton Moyer, Brian Voorhees, and myself.
Yeah, Spencer, that's way quiet.
All right, let me see if
You had it working for 384. Or no, you didn't. You guys presented live, didn't you?
We printed.
Yeah, I mean, it's just the thing is quiet. I don't know if I.
It is brewing.
Here. Yeah. All right. If I hit play, can you guys hear it now?
We can hear you. This is our final presentation.
Yeah, not bad. I mean, I just need to turn up the volume a little bit.
All right, thank you.
The issue is that it's complicated and manually intensive for the brewer. Home brewers have little control over their brewer's internal precision, and they have to pay a lot more for pretty stainless steel, but get little in functionality. Look at Spencer and I in this photo. He's training himself to drain our grains and to continue brewing. In an era of dynamic technological innovation, brewing beer in the home is ready for an upgrade. Herein lies the Brew Lab.
Brewing beer can be done in two different ways, all grain and extract brewing. When all grain brewing, water and grains are mixed to extract sugars and create a liquid called wort. Extract brewing is performed with powderized wort that has been created at a larger scale and generated for a specific recipe. Our system will be designed to be capable of all grain brewing for maximum control over the brewing process. The first step in brewing is mashing the grains. This is a process of extracting the sugars from the different grains used in any specific recipe for beer. When mashing, the grain and water mixture is kept at a specific temperature between 145 and 160 degrees Fahrenheit for between 60 and 90 minutes. This mixture creates the wort. During the mash, temperature and pH are both measured and maintained based on the recipe. The next step is the boil. This step extracts bitterness, aroma, and flavor from the hops specified by the recipe and concentrates the wort. Hops are added at specific times for the desired effects, an instance where the brewer is required to manually intervene in the process. Missing a hop addition or adding hops late can result in a less desirable beer. During the boil, the specific gravity is measured to determine the efficiency of the process and to help determine the final ABV of the beer. This is a manual measurement done by the brewer. I'm using a refractometer to measure specific gravity in the picture shown to the right. After the boil, the wort is cooled either with an immersion chiller or a counterflow chiller. The wort is cooled to the temperature required by the yeast strain in a recipe, typically 68 degrees Fahrenheit. This part of the process requires a 100% sanitary environment. In an automated system, this process requires no human intervention, eliminating the possibility of contamination.
Shown here is a list of requirements that we believe a consumer will ask of an automated brewing system. Before the brew begins, a brewer will need to specify all the steps of your recipe and then load the ingredients into the system. During the mash, the system will automatically recirculate and heat the wort as required by the recipe, as well as modify the pH. The boil intensity will be automatically adjusted and the hops will be automatically added. The wort is then automatically cooled and pitched to the fermenter. The common theme here is that everything is performed automatically. Our system will be designed to perform these actions and work off of the predetermined recipe as specified by the brewer.
Our system is designed with the requirements needed for the perfect brew, being produced in sanitized stainless steel and food-grade plastics, having an easy interface able to change the brew factors, runs on common household power, and before being sent to market, it'll be tested to make sure it has the same quality measurements as those done by hand for the volume, temperature, and specific gravity, with the system being a much safer process than the handmade alternative.
Our process utilizes a two-tank system. The valves are positioned in such a way that we have 3 specific fluid flows. Recirculation in each tank individually as well as a figure-8 pattern. This allows for a recirculation mash, a whirlpool hop addition, and a sparge at the end of a mash. Also shown is the location of the counterflow chiller, as well as the whirlpool and sparge port on the mash tun. The final step will be draining the boil kettle into the fermenter, which will be performed by gravity.
Shown on this slide is a diagram of our WBS. From the WBS, a responsibility matrix was derived and progress was tracked. This spreadsheet helped us compare our progress to the schedule and determine whether we were ahead or behind. Our schedule is highlighted here. The schedule is broken down by semester as well as by task. The WBS progress was tracked and compared to the 30, 70, and 90% goals that we set for ourselves. The prototyping is broken down into a similar schedule for the spring semester.
The boil kettle makes use of a pressurized system. This increases the boiling point of the system, resulting in better extraction of bitterness from the hops. The drawings also include a port system for the necessary sensor suite and utilizes a conical bottom to facilitate gravity draining. The system also includes a whirlpool port for whirlpool hop additions. The system also makes use of an automatic hop addition
Did
device.
we lose them?
Hop additions
I can't hear.
The machine utilizes a similar design that incorporates a sensor suite. The machine includes a basket shown to the right that filters the grains and allows for a grain bed to settle. The basket incorporates large handles to facilitate easy removal.
The system also makes use of a sparge port at the top for recirculation purposes.
The system is designed to allow for modular takedown for easy repair while being decently compact. Both stainless steel containers can be pulled out and disassembled for easy maintenance. The liquid injectors are positioned to be easily filled and to easily add syrup and lactic acid to the brew. The chiller, sensors, and valves are all condensed into a simple connecting hydraulic circuit that allows for simplicity and reduced maintenance in the overall design. All is stored within a steel frame on caster wheels to be self-contained and portable within a garage.
2 electrical circuits were needed for this project. The first, shown on the left, is a circuit that will send a PWM signal to the valve motors. These solenoid valves require a full load current to open and then a smaller duty cycle current to stay open and not overheat. This circuit will be tested in the spring to verify its performance. The second circuit is designed to open and close a relay. This circuit will allow an Arduino output to apply 12 volts or 0 volts to a relay. A PID controller will be programmed to allow this relay to drive an electric heating element and heat the wort in our system to very specific temperatures.
The sensors were all carefully selected to withstand the environments they would be subjected to. The pH sensor was required to withstand an operating temperature of 160 degrees Fahrenheit. This sensor will be mounted in the mash tun. The thermocouples will be easily integrated into an Arduino. Op-amps will be used to amplify the sensor signals to be read by our microcontroller. The gravity sensor has not been identified at this time. Several options have been identified: a total dissolved solid sensor, a capacitive sensor, and a specific gravity sensor itself. These options can all work within an Arduino. However, identifying the most cost-effective solution has proven difficult.
The user interface is designed around an Arduino Mega. A 7-inch touchscreen will be used as a GUI for the brewer to specify the parameters of a brew and for the system to display vital information. The sensors and valves will all interact with the Arduino, and the outputs from our microcontroller will be able to directly control the automated parts of our system.
In our project, we see that the parts cost more due to the improved quality. Features such as the pressure vessel design and fully stainless steel construction make this system built to last many years of easy brewing. With a cost of $3,000, this system is not achievable on our school budget.
This is the model that we will be constructing for our proof of concept. Since our pressure vessel design has a BOM cost of $3,000, we decided to simplify the design to minimize costs, avoiding the pretty stainless steel parts and going for more economy materials. The main differentiators being that the mechanical system will be made cheaper. Mainly prefabricated materials will be used to make the pot, and less costly materials will be used to construct the cart that our apparatus will be mounted to. Cheaper options will be used for the valves, still keeping the electrical systems functional.
The prototype we are creating is drastically cheaper and easier to produce. The parts being used in the prototype are not held to the same standards as the final project, and the appearance will be overall less important in the prototype design. We also are abandoning the pressure vessel style system in favor of creating the system out of pre-manufactured materials. This will bring our budget down from the multiple thousands to below $1,000. We expect the cost to lower more as we continue to refine our ideas over winter break.
The test plan will be broken up into 3 parts, the first of which is testing. Each of the individual components will be tested before we go and purchase our entire bill of materials. The second step in testing will require the assembly to be built and the manual testing of all the components involved. At this stage, a manual brew will be performed, and we will ensure that the system works properly. The final step in testing will be the automation stage. In this stage, an automated brew will be performed, and the overall brew will be evaluated for quality. During this time, the system will be monitored throughout the entire process to ensure performance, and once again, the final product will be re-evaluated for quality.
We are expecting to revise our prototype throughout the testing process and to have issues integrating the electronic systems. Throughout the test phase, some issues that can occur include an inadequate part selection, where a part does not meet the requirements we have of it. Sensor calibration could also present a problem, as well as difficulties modifying the pots and the program. Other issues that can occur also include issues with the beer process itself. One main problem we foresee is a phenomenon called doughing. This is when the grains ball up and prevent the mash from reaching its peak efficiency. We are anticipating these issues and are actively thinking of solutions that may be needed. Thank you for attending our presentation. Questions will be answered at this time.
Great presentation. I have a question for you. You mentioned that you add the lactic acid to the solution.
Yeah.
Why?
So when you're brewing, the mash liquid it has a peak efficiency at a pH of around 5.2. A lot of times, depending on the water that you use to make to do your brewing, the pH is going to be 5.6 to 5.8. So a lot of brewers will add a calibrated amount of lactic acid per volume of fluid in the mash to bring that pH down to 5.2.
And then how do you connect in automation the source of lactic acid and your pH control signal that you open the valve for the right amount of lactic acid?
So we're going to use a, oh yeah, go ahead, Corbin.
I'll say I can handle this since I was in charge of this. So lactic acid is actually added using a chemical injection pump. The typical, I'm sure you've seen them before, the typical U-shaped tube. It's got two paddles on it. Stepper motor turns the paddles against the tube. It forces out a predetermined amount of volume of the lactic acid. Like we said with the pH sensor, we'll just monitor the pH throughout the process. We'll add, and as we're adding and recirculating, we'll be able to constantly monitor the pH. We'll have a general idea of how much we need to add just based off of some simple equations. We will fine tune it, so to say, by monitoring the pH sensor as we're adding. Once we've reached that level, we just stop turning the chemical injection pump. And
the manual. Yeah, thank you.
Of course.
All right, can I have a question? Okay, good to see you, Spencer. Hasn't been able to see you for a while, okay? All right, just a quick question. When you mention PID, I get excited, okay? So you mentioned you want to use the PID control to control what? What are you trying to control?
The temperature, we have a 120 volt electric burner. So it's a 1550 watt burner that screws into the side of the pot. And we're going to use a PID controller to tune it to specific temperature. So measuring the temperature of the fluid with a thermocouple and then heating it. So when you mash at a temperature anywhere from 145 to 160 degrees Fahrenheit. That needs to be maintained for like an hour. So you can't just apply 120 volts to the burner and just let it run all night. We're going to use a PID controller to tune to specific temperatures. And that's different per recipe. Some recipes call for 154.2, some of them call for 156.0. So it's a pretty precise process. So that's why we're using that.
So that's going to be you decided to implement this like a digitally using like a piece of code and stuff like a hardware. Okay.
Yep.
All right.
And that can be tuned too in the future. So our burner right now is 1550 watts. If we up the burner to say 3500 watts, that's just dependent on the circuit that you're hooked up to in the home. 1500 watts will work on a 15 amp circuit in the house. But if we up the burner size, we can tune that PID controller just to be a little more accurate depending on the burner too.
Hey, thank you very much, guys. Virtual clap. All right, so we're at the point where I have small breaks scheduled. I think we're going to do the same thing, try to keep us on track. We are running probably 15 minutes behind schedule, but that's okay. These are great questions. At the very latest, we're going to wrap up by 4:15. I'll try to make my closing remarks as brief as possible, so probably 4:30 at the latest, maybe 4:20. So 2-minute break. The host needs a restroom break, to be honest. So, I'm sure others do as well. So get a drink, stretch, take a break, and then just 2 minutes we'll reconvene with group 9. And then just a reminder to all the other groups, please upload your PowerPoints. Still not seeing all the teams. I'm missing 2 from 391, and I'm missing the both teams from 392. So please upload them so I can have them all.
About 5 minutes, Ed?
What's that?
5 minutes? 5 minutes instead of 2 minutes.
5 minutes, it will be. 3:35, we will reconvene. Okay, good suggestion. Okay, 5 minutes. Thank you.
Yangzu, how's life? Your family treating you good?
Make sure everybody can hear you, okay? Just be aware of that, okay?
It's fine.
Okay.
Everything good? Family is good? Children? Wife? And you are not in trouble?
Never in trouble.
That is good.
Okay, I'm back. 6 minutes, sorry. It took me 6 minutes. All right, so we are ready for Group 9, Eco Wing.
Yep.
Okay.
Can I start?
Go ahead, Nick.
We are group number 9. Our project is the Eco Wing, and in our group it's me, Nick Martino, Jacob Demler, and Cameron Aspey, and our advisor is Dr. Gamari. So a little bit of background on the topic. Due to the truck's size, shape, weight, it leads to poor fuel economy when compared to smaller vehicles. You can tell this from the low gas mileage that these trucks get. Overall, it is said that the drag coefficient for the Ford F-150 is estimated to be around 0.59 when traveling at 60 miles per hour, but for other smaller compact cars, it's said to be about 0.3 to 0.4. It is also said that a good amount of this drag is caused by airflow flowing over the top of the truck and getting trapped inside of this truck bed. So to start off this project, we did a little bit of research on previous studies of add-on devices that reduce the drag coefficient. The first was a rear roof garnish, which overall helped to reduce the drag coefficient by about 2.4%, and an example of this is shown in the black car above. The second idea we found was more helpful. It was an aero cap, which had a rear incline angle of about 12 degrees, and overall it helped to reduce the drag by about 16.2%. An example of this is shown with the red car.
Our project began with the intent of designing an adjustable pickup truck bed cover. This original idea would have been designed in a way that optimizes the aerodynamic efficiency by implementing a slanted cover. This would have been fully enclosed to keep all the goods stored inside the bed dry and locked. However, the project eventually evolved into a wing which would attach to the bed rails while also providing reduction in aerodynamic drag. This would also retain almost all of the bed space for larger items. We found that there have been studies in the past on add-on devices to improve fuel economy. However, the Eco-Wing has a minimalistic design and still offers improved gas mileage. The Eco-Wing will be easy to install with just a few bolts attaching to the existing bed rails.
So seen here is the model of the truck and the Eco-Wing, which was modeled on SolidWorks. It was later assembled to attach the Eco-Wing to the back of the truck bed. There were some requirements that were focused on throughout the completion of this project. These requirements were separated into two subcategories, the first being the air resistance and the second being the mount installation. When focusing on air resistance, we felt that the system should redirect the airflow over and around the truck bed. We also wanted to find a drag coefficient that was much lower than the initial value of the truck. When focusing on the mount installation, we wanted to make a system that would allow for easy installation and disassembly of the project without damage to the vehicle. This system consisted of a mounting bracket that was attached to the bed rail using clamps. The three wings would then be attached to the mounting bracket using nuts and bolts. Overall, we wanted the installation of this project to allow us to still use the maximum capacity of the truck bed without blocking any of the storage room.
The construction of the Eco-Wing will be a molded fiberglass skin to keep the device light. This skin will have a specified length and angle with respect to the truck cab in order to provide the best aerodynamic efficiency. These parameters, the length and the angle, will be determined through simulations as well as physical testing. In order to withstand crosswinds, this fiberglass skin will be supported by box tubing, which will be aluminum. This box tubing will also provide a skeleton in which the EcoWing can be mounted to the already existing bed rails which come standard on most pickup trucks. In turn, this means that the EcoWing will be removable without damaging the vehicle or its paint. The EcoWing will provide a reduction in aerodynamic drag while retaining a pickup truck's main purpose. Testing would need to be performed in order to prove the safety and stability of the EcoWing. Real-world conditions will be studied in order to ensure that the performance matches the performance observed in the lab. However, in our project, we will be analyzing the data from the simulations and comparing that data to the data collected in the wind tunnel.
Looking at our budget, there will be very little cost to the university for completion of this project. The only real costs we'll be facing are for the 3D printing of the scaled EcoWing and the scaled model of the truck. The total cost for the university will be around $95. We also made a budget for if this product was fully manufactured. This budget includes prices for materials and labor. According to this, it would cost about $334 to make one EcoWing. At this price, we'd plan to sell them for about $400 each for a profit of around $66. This price would most likely drop if taken to large-scale production, as most of the cost comes from the fiberglass sheet used for the wing. At large scale, we'd be able to purchase large amounts of this material in pellet form to be melted and formed, rather than purchasing sheets, which would definitely lower the cost of that portion. With a lower cost, we'd then be able to increase profit and possibly decrease the price.
This chart shows the work breakdown structure of the EcoWing project. There are three main subgroups: mechanical, testing, and management.
According to the schedule we created at the start of the project, we're currently on track. We have so far conducted preliminary testing on our first design using simulations. We plan to order the scaled model and conduct more simulations over winter break. Next semester, we'll conduct our wind tunnel testing and finalize a design. We're not sure whether we'll have the resources to actually construct a full-scale prototype to do the last stage of the material testing, but if we were ever to move this project to the market and actually produce it, this is testing that would need to take place. Our testing plan has two stages. The first stage is simulation. I won't go into detail here because we'll go more in-depth on later slides. The second stage is wind tunnel testing. For this, we will order a 1:50 scale model truck. We will use propylene glycol within the wind tunnel to create a smoke-like substance to get a better visual of airstreams. We'll focus mostly on the bed and tailgate of the truck because this is where the EcoWing will affect air currents. After testing the truck by itself, we will 3D print a model of the EcoWing scaled down to fit the model truck. We will then test this in the wind tunnel to see how the EcoWing changes the air currents and get a visual of how the airstreams change.
The simulation was going to be performed using ANSYS Fluent until we learned more about Discovery AIM. ANSYS Fluent would have given us only two-dimensional results, but because Discovery AIM doesn't utilize meshes, the system could be done in 3 dimensions. The truck design was imported to Discovery AIM and was tested with a constant wind speed of 25 meters per second, which is around 56 miles per hour. The box that encases a truck is 4 meters longer from the front end and the back end of the truck. This allows us to see the streamlines that the truck will give us. We managed to get 2 simulations done this semester. One simulation does not have the wing attached, and the other simulation does have the wing attached. Because of the limited processing power that a student edition allows, each simulation took about 2 hours to complete. The wing design shown in the simulation is not our final design. Many more tests will be conducted with different angles and different lengths of the wing until we find a solution that best fits. I plan on running more simulations over the extended winter break so that when we come back, the wind tunnel can be utilized right away and give us some real-world results. Here are the results of the 2 simulations. The top row is a side view of the trucks, and on the bottom row is a top view of the trucks. The right column has the wing installed, and the left column doesn't have the wing installed. It can be seen here that when the wing is installed, the streamlines reconnect sooner, resulting in less drag. This is caused from a more streamlined shape that the wing creates. Here are the results of the velocity with the field flow included. It can be seen from the side view that when the wing is installed, the velocity gets back to the initial speed much faster than it was without the wing. The same is for the top view, in that the speed stabilizes much faster with the wing installed than without it installed.
So overall, it was found that by adding the Eco Wing into the simulations, it can help to show that it is possible to alter these streamlines of the wind flow, which in return can help to better increase the drag coefficient in the truck bed. Overall, we feel that the project was a success, for we learned many new things from the research and simulations that we ran. Next semester, we look forward to furthering this understanding by doing wind tunnel tests and other simulations.
We would all like to thank Dr. Gamari for all of his helpful insight throughout this semester.
And here are references. Does anyone have any questions?
Okay, I'll go first. Okay. So I have two comments. The first one is that it's actually a very meaningful project, and you guys have to. It's definitely not easy to do the full-scale testing, but at the same time, simulation plus sub-scale testing would still be able to generate a tremendous scientific results and insight into this problem. So it's definitely, I think you guys should focus on simulation as well as sub-scale testing. And talking about sub-scale testing, it's actually very commonly used in industry for many research, and like a Boeing, or they use lots of things. It can yield some great results. You just have to understand that there's a translation, like there's a conversion from sub-scale results into full-scale results. There's like those ratio, like square or something. You can definitely find out. I did similar things when I was in industry. So it can, like I said, don't underestimate the power of sub-scale wind tunnel testing. You can definitely convert those into full-scale results. So that's my first comment. The second one is that what do you guys think of why Ford is not doing this?
I think the reason why a lot of manufacturers don't do this is just because of the way it looks. Like the design with the aero cap, it just looks more like a car, and it doesn't have like the open bed for as much storage. That's why we're trying to keep it a really small design. Okay, so you think that's kind of the benefit, the gain, kind of overrides the kind of the possibility of losing the appeal of a product, right? Something like that. So it's a compromise. So that they decided to just give up some fuel efficiency instead of try to make sure at least it looks like appearance to be very appeal. So okay, so that's my question. Okay.
Yeah, there are aftermarket companies that have small garnishes that stick off the back of a truck for slightly better aerodynamics, or there are companies that produce the aero caps, which cover the whole bed of the truck and slope down, which gives much better fuel economy. But the issue with that is it's an entire cover, and it cuts down on the space allowed in the bed of the truck.
I see.
And it reduces the ease of access to the back of the truck a little bit, whereas our design is kind of a middle ground between the two, where it's still easy, you still have a lot of storage, but it gives you better fuel economy than the small wing would.
That's great. So just, I think it's a really interesting project. Just focus on the sub-scale. Hopefully you guys can leverage the wind tunnel and get some meaningful sub-scale testing results and try to extrapolate that into like a full-scale results. I think you can draw some pretty interesting conclusion and use that to modify your design.
Thank you, Dr.
Ed, my question is the wind tunnel fully operational for them?
Are you asking me? I don't know, Dr. Gamari. Do you know?
The wind tunnel is operational. Some of the features, and like for example, if you want to measure the amount of drag, the balance, we are not sure if we can use it still. I mean, there is nothing like unoperational about it, but we are not sure if it's calibrated. Our aim from the beginning was not to focus on the calculation. We are going to mainly focus on the visuals and qualitative results from the wind tunnel. We can at least see the streamlines in wind tunnel. And as long as we can provide a model that matches the experimental observation, then we can probably focus more on the model, because that's where most of the time is going to be spent, just tweaking the model, the curvature, the angle. Once we have some rough idea about how it's going to probably look like, they're going to make a prototype on a maybe 1 to 50 scale down model, put in the wind tunnel, do some basic testing. And I don't know if we can go to the full scale at this point, but we may stop there right in the wind tunnel.
That is the real experience for them. Thank you.
All right, thank you very much, guys. Virtual clap. So that that concludes our senior projects 1 team. So we had 9 groups go for ME 391, EGR 391, EGM 391. So great job to all the 391 teams. Know that you're halfway there, and kind of echoing what other faculty members have told you, use your break wisely. So you know, we'll see you all again in the spring for hopefully conclusion and testing and prototypes and all that great stuff. All right, so now we're moving right on to, we have 2 ME 392 teams that have started way back in January. It must seem like forever ago for you guys. You know, you've been working for 10, 11 months on these projects, and you had a whole summer as well. So now, you know, just of course the faculty knows these are teams that are done. They're finishing, they're graduating, hopefully, if you pass. So we're going to start right with group 1 of ME 392. So the automatic barbecue grill.
Okay, I'll be sharing my screen.
Okay.
Good afternoon, everyone. We are group number 1 of senior project 2. Our project is automated barbecue grill. The group members are Hamid Al-Ghammas, Ibrahim Al-Banasir, Saeed Al-Trad, Hassan Al-Hudar, Fahad Al-Mangour. Our advisor is Dr. Kalim. We will start by introducing our agenda for this presentation. The agenda is as follows: overview design, other product in the market, drawings, project description, requirement, specification, WBS, calculation, cost, acknowledgement, and finally, reference.
Here is an overview model of our complete design. In the following slides, we will discuss more about how we were able to assemble them together and mention the parts that went under change compared to the previous semester. However, due to limitation on time, we will only focus on the key components of the project.
Here is a similar design to our project in the market. Figure number 2 shows our frame design. We have the number of each part, description, and the quantities. The walls will be welded to the base of the frame. Figure 3 shows the frame with the protective housing, and the point of the protective housing is to increase the safety of the design because we have a rotating equipment. Figure 4 shows the frame, the protective housing, the legs, and the shaft of the gear. In the close-up detail view B, you can see where the shaft will be. And we have 4 rectangular hollow legs. And the reason of that is to reduce the overall weight of the grill. Figure 5 shows our idea of how the skewer should be. The skewer needle is 16-inch with a diameter of 0.15. And the needle is 6-inch, and that is made of wood. The gear will be placed between the needle and the handle. As you can see, the gears will be mounted on the skewers to ensure the constant rotation. The following drawing shows the complete assembly, including the skewers, the motor, the chain, and the motor housing. Please note that section L shows the shaft and its gear. On the other hand, section J shows a close-up view on the motor and the motor housing. Lastly, section H shows a close-up view on the support of the motor housing. Please note that the support will be welded as well to the leg. Furthermore, the support is also a rectangular hollow tube.
Our project focuses on creating a model for an automated barbecue grill that will help in reducing human interaction with the grill. Our model consists of several mechanical and electrical components, such as gears and chain. Our model will use these parts to generate constant rotation to the skewers. Another aspect of our project that we aim to achieve is the health of the workers. As we know that grilling process requires long duration of standing in front of the grill and repetitive movement. These two reasons could generate health issue for the workers in the long run, such as lower back pain. In terms of target customers, we are targeting restaurants because time is the most important factor when it comes to business. Using the auto grill will save the restaurant crew time, also will help to reduce number of staff, which will reduce the operation cost. Requirement. The skewers will be rotating at a certain RPM that would allow the meat to be cooked for the recommended time period. One of our goals is to maximize the capacity of a skewer that our model could handle. Moreover, our model's capacity at least is 15 skewers. The frame would be able to handle different types of meat. The machine will be designed to reduce the amount of human interaction as much as possible.
Specifications. We changed the material that we are using to build the grill from stainless steel type 304 to our new material, which is 1075 Cypric steel, because it's suitable for all welding methods and more cheaper. The design will include sprocket gear and chain. Sprocket gear to transmit rotation from motor to chain. It has diameter of 1/4 inches. Also, we have set screw to secure on the shaft. Moreover, we have a chain of 8 feet length rotating constantly to allow rotation of skewers. The gear will be connected to an electric motor to provide rotation installed in the shaft. The motor that we have is DC motor compact round face. The shaft size 1/4 inches. Here is a general model dimensions. Height of 29 inches and width of 48 inches and depth of 17 inches. Here is the work breakdown structure for our project. We divide it into 5 phases. Each phase has a several number of tasks and ends up with milestones, which is the goal for each phase.
For our heat analysis, we were mostly concerned about 2 things. The first one is the temperature that the motor area will be exposed to, and the second one is the temperature of the skewer. To tackle these issues, we had to assume that it is a steady state problem and it's one-dimensional. And the reason for that is that the thickness of the wall shown in figure 7 is much less compared to the width and height of the wall itself. Figure 8 shows the thermal resistance circuit that we applied in order to reach to the second temperature, which is the outer wall. On the left side, you could see some of the equations that we use, including the heat transfer of the radiation and the thermal resistance of conduction. The heat transfer of the radiation was used because the temperature is going from the coal that is placed on the frame or the base of the frame, and it's transferring to the food and to the walls by radiation. And that's the reason we use the pure radiation. For the resistance of for the conduction resistance, we had to use that to figure out the resistance going from temperature 1 to temperature 2, which is the inside wall to the outside wall, in order to figure out the temperature close to the motor area. As you can see on the left side, we have some thermal conductivity for the material that we are using and the thermal conductivity for the actual food that we are cooking. The temperature of the coal, based on some research, it showed that the range of grilling temperature is from 170 Celsius degrees to 200 Celsius degrees. And we had to convert it to Kelvin in order to complete the calculations. Based on the numbers that we had, the results are as follows. The heat transfer by radiation is 2,766, while the temperature at the wall, at the outer wall, is 469.9 Kelvin. The motor area, it will be exposed to around 469.8 Kelvin, and the reason for that is that the wall is close to the motor. It's around 1.5 inches apart from each other. For the temperature of the skewer, we assume that it is approximately the same as the temperature of the food, because the thickness of these two items is not very big. Lastly, the temperature approximated at the skewer is 469 Kelvin, and that means that it is very hot temperature for a person to touch it by hand. As a result, we had to implement a wooden handle to the skewer. For the torque analysis, we wanted to determine how much torque the motor should be applying in order to maintain constant rotation of the skewers. On the left side are some equations that we used and some known variables. It is important to note that the angular velocity could change based on the amount of temperature applied to the food on the frame. Based on the numbers that we have, the result is that the torque needed by the system is 0.1067 Newton meter. For the buckling analysis, our aim was to determine whether the legs will be able to handle the load applied on the system or not. Figure 11 shows an illustration of how the load will be applied. On the other hand, figure 12 is another illustration of the area of the legs. As mentioned before, the legs that we are using is a hollow rectangular tube. On the left side, you could see some of the equations that we used. Some important equations to pay attention to is the slenderness ratio and the tangency point. Based on the results, we could determine whether to use the Johansson equation or the Euler equation. Another important equation is the critical stress, and it shows where the column would most likely fail upon applying the load. Another equation is the safety factor. Some known variables are the load that will be applied to the system, the yield stress of the leg, their total area, and the Young modulus. It is important to note that the legs will be treated as a bent fixed beam, which means that it will be welded from one side only. Based on the numbers we have, the effective length of our legs is 16.8 inches. The slenderness ratio is much, much lower than the tangency point. As a result, we use the Johansson equation. For the critical stress that the column will fail at is 31,599 psi. The critical force is 3,974. Finally, we wanted to determine the safety factor of our design, and based on the numbers that we had, it is 4.75. And as we all know, as long as the system has a safety factor of 2 and above, it is considered as a safe system.
Here's our cost table. I will point out only the most important part of it and mention the part that were changed compared to the previous semester. First thing to mention is that we have 2 different gears. The first gears that we need 20 of them that cost us around $200. We're gonna use them for the motor and skewers. The second gears that cost us around $25.40. We're gonna use it for in the end of the frame. Then we have the chain around $41. We have electric motor cost us around $110, and the material for $102. We have 2 kind of leg, one of them 6 feet and the other 3 feet. The 6 feet cost us around $18, the other around $11. The welding per hour is $21. We need 3 hours for to complete our project, so that cost us around $63. The skewers around $24. That cost us the total amount $593.47. At the end, we would like to express our thanks to Dr. Kalim, Dr. Bidners, and Dr. Gamari for their advices and guidance throughout the project. Here's our references, and thank you for listening.
Okay, we have time for 1 or 2 questions.
Hello?
Anybody want to weigh in on any questions for the barbecue grill?
What did you physically build?
Sorry, could you repeat the question? I wasn't.
What did you physically build?
We weren't able to actually build the project, but we were only able to model.
Not a single piece?
No, we weren't able to do that.
And that was intended?
Yeah. At the beginning of the semester, we had 2 choices. Either we stick with the previous plan, which is actually building it, or decide not to build that and focus on the actual model in SolidWorks. And the reason for that is it's with the current circumstances, it's unpredictable with the COVID-19, so we weren't ready to take the risk of doing that.
As the instructor, I gave them the option. I said if they want to pursue the prototype, they could, or if they want to complete the design. But I did say if you're going to choose the latter route, it has to be a totally complete design, complete drawing packet, analysis, everything's ready to build. Because other teams are putting in the effort of building prototypes and testing and all that, but that was the option that I gave them, and it's most likely going to be the same option I'm going to give the current 391 class as we proceed into the spring, because unfortunately I don't see COVID going away anytime soon. So there's a lot of teams that are choosing to build their prototype, and we did get guidance from the university that they can do it safely, as long as they're wearing masks and social distancing, but those teams that choose not to build prototype. It's no longer going to be required, at least for this school year. But with the knowledge that they're going to have to put in the extra effort with complete analysis and the CAD drawing packet and all that. So, yeah, just to kind of maybe give them a little, or give you a little background as to why they only finalized their design this semester.
Just following on Dr. Zhu's comments, because what I saw in terms of the model is pretty much similar to what I saw at the end of 391. What did you achieve? Like what did you change since like 391, since May?
We worked on the general dimensions of the previous one. We completely changed the length and the width and overall the weight of the actual dimensions. Furthermore,
I can't hear you.
I hear,
go ahead.
I hear a motorcycle somewhere.
Yeah.
Okay.
Furthermore, we added like a protective housing for the motor holder for the motor on the side, in order to make sure that it's not touching the actual walls of the frame. That's for
but if you wanted, you could have built a prototype, right?
Well, let me just say something. I mean, yes, it's difficult to build the whole system, but let me demonstrate how to control a motor. Let me demonstrate how to control this, how to just do those kind of basic things. I mean, as a senior capstone project, that's all I want to say, that's all.
Yeah, so I've been pushing this team, maybe I'm on, not to put you guys on the spot, but I think they have shown progress throughout this semester, especially in their drawing packet. The drawing packet that they submitted in the week 7 of the semester was lacking. So I've been really working with them over the last month, and they've been, adding to it. Through the 384 course, they've been looking at test plan. So I said, look at all the ways this can fail. It can buckle, a user can burn themselves on the handle, the motor can overheat, right? So these are all things that they have thought about this semester. I'm not sure if I try not to get feedback at this forum, but I kind of warned you guys about this a few weeks ago, that I think you're doing a lot of work behind the scenes, but I don't know if it's coming out in your presentations, that, how much work you have been doing. So yeah, I don't know if the same thing came across today. That's why you're getting similar questions along those lines. But okay. All right. Well, thank you guys.
Thank you.
Thank you. Virtual clap. All right. So we're going to move on to our very last team of the evening. Thank you for your patience. Thank you for, I know we're going past schedule, but I'm going to blame some of these teams not listening to me. I said 9 to 11 minutes. And that last team went 15 minutes. You should have re-recorded it. And I know earlier teams did too. Chris, he went like 13 minutes. So for next semester, I'm really going to get on them to stick to their time. Otherwise, I don't know, I might cut them off. Maybe that's a disadvantage.
One of my group, Bryce, they asked me if they can go like maybe 2 minutes above the limit. And I told them, based on my experience from the past semester, maybe past 2 years, we usually end up saving some time, especially if you are not the first group. Everybody goes below the time limit, but today was a little bit different. Like everybody was planning just, probably that's because most of groups have a lot of accomplishment. They had a lot to kind of talk about. Yeah. Part of the blame goes, I take responsibility for my groups. I told them, it's okay. Go 2.5 minutes above the limit. That's fine.
That's okay. I mean, hey, a lot of knowledge was learned today and a lot of good feedback. So if we go 15 minutes past my schedule, I'm okay with that, right? I mean, that's fine. We're still, and great questions too. Some of the times I could have cut off the questions, but I wanted to hear their responses. So, instead of 3 to 5 minutes questions, sometimes we're on 6, 7 minutes, but it's all good. Okay, I'm going to officially introduce our very last teams for the day. Group 2, Senior Projects 2, Euro Dark Weapon System.
How you doing, guys?
Okay, Matt, you're ready to go.
Can you hear me?
Yeah.
Okay. I'm just going to play. I want to make sure I have all my audio outputs set up properly, so I'm just going to play a quick snippet of a song here, and let me know if you can hear it. You hear that?
Yeah, you got it, Matt.
Okay.
That's very. Did you hear that, Ed?
Yeah, it was very low.
Very low.
That's okay.
Very quiet?
Yeah.
Yeah.
Okay.
That's got a professional audio studio. It looks like.
Yeah, I got a mic recent. Okay, so let me just share my screen here. Oh, that's not the right one. There we go. Okay.
We'll see if we could hear your video.
Okay. Okay, so I'm going to play our presentation now.
Turn it up.
Yeah, not so good.
Nope.
Did you
Too
share
quiet?
the audio? Yeah. Did you share the audio? You shared. Yeah, a lot of teams have been making that mistake. Share screen, and then at the very bottom left, you have to enable share audio.
Oh, gotcha. Okay. Share screen.
You may have to stop sharing and then share again.
All right. My bad. I tried to prepare for this in the meantime, but I guess I didn't quite do it right, huh?
That's okay. Yeah, so share screen, very bottom left, share computer sound. I should take a screenshot of this to show people.
Allow. And would that pop up on the
On the whole window where it says share screen.
Okay.
I should have started with this actually.
Yeah, I'm sorry about that. I was trying to prepare. I wanted to make sure everything went as smoothly as possible, but I guess
That's okay. Okay, so did you hit the share audio this time?
I didn't see anything pop up for that.
Here, stop sharing for a second, please. I'll just show you real quick.
Okay.
So see this little button right here. Like when I hit share screen, this whole thing comes up, and then there's a little button right here, share computer sound. I suppose I could have started out the presentations with that.
Yeah, I do not have that option.
I mean, your video was playing. It was just quiet. Like I said, only if you could put the audio output higher on your system.
Yeah, the audio is maxed out on my computer right now.
Mason, do you have the file?
That's the emails to me. I can play it on mine.
Yeah, we'll be able to send it over an email. It's like over a gigabyte, I think.
Wow.
Google Drive.
When you
Yeah,
press,
you know what?
does that window come up, Matt?
No, because I'm in the. I think I'm here. Let me try something really quick.
I mean, worst case scenario, you can load the PowerPoint and everybody just talks over that in real time.
Yeah, it doesn't bother me.
Where did Matt go?
I think he's gonna try and rejoin through the app, maybe.
Yeah, I think it's kind of along in a different way.
Yeah, like if you just click on the link and you use Zoom website, I think everybody sees the same interface.
All right. I think it was because I haven't been using the online or the app. I've been using the web-based client. So I think that could be why.
Switch over.
Yeah, I can see it in the app on mine.
Okay.
Did you have the button this time to show computer sound?
Okay, now I can't hear you guys.
We'll try playing it.
Okay. I'm really sorry about this, guys.
Try playing it now.
To keep track of the amount of rounds fired from a firearm. Good afternoon, everybody. Good afternoon, everybody. We are Zero Dark Weapon Systems, and we have been working on designing a first-of-its-kind weapon attachment that uses vibrational frequency to keep track of the amount of rounds fired from a firearm. The device displays information such as cardinal direction, round count, and magazine count on a HUD that simply attaches to the rail system of an AR platform rifle.
Okay, so let's meet the team. First, myself, Samantha Bitzer. I'm the project manager, also in charge of reports, alongside Mason Iovino with calculations, analysis, and testing. And we also have Gage Crisanda with 3D modeling and the physical build, Nick Gatos with 2D drawings and presentations, Matt Escott in charge of logo design, logistics, and physical build, Shuk Alfalcali with cost analysis, and of course, Dr. Carol Bador, our advisor.
Looking at the final design, it can be seen that the original key design concepts are all still present from our original design. Some of these features are a quick detach rifle mount system, a heads-up display visor, O-ring seals on all removable covers, a high impact rated Lexan screen protector, and all stainless hardware. The device utilizes a small OLED display which is efficient on power to give the user feedback from the inertial measurement unit. All systems are run on a rechargeable 9-volt battery. Looking at the two images here, you can see that the device is in its completed state, as well as an exploded view which shows all the components. Looking at some changes to the final design, we integrated a set of 3 momentary buttons for screen controls and to control the device's power. The battery housing was made a separate piece from the original housing. This was done in order to simplify 3D printing support structure in our initial testing, as well as to make components easier to install while prototyping. The inertial measurement unit mount was moved from the battery housing to its own individual mount, which mounts to the steel plate within the device.
On this slide, you can see a non-functioning 3D printed example of the housing of the round tracking attachment as it is attached to the Picatinny rail of an AR-15. To the left, you will see an image depicting what your sight picture would look like while the device is attached. In the middle, we have an image depicting the size of the device. And finally, to the right, we have an example of the mounting mechanism for the device. Future iterations can be enhanced to produce a smaller overall form factor.
Our goal is to equip our military with a state-of-the-art weapon attachment that will provide them with the correct number of bullets left in their mag while engaging in a live-action firefight to increase situational awareness. This advantage will ensure our military is top tier and will provide them with the latest technology to improve their chances on the battlefield. Our group did extensive research on designs similar to ours that are already on the market. As you can see, our design all the way to the right had checked off many more boxes than all 4 of the other designs that have already been patented. Zero Dark Weapon System stands out and above from the rest.
Looking over the requirements set forth by the team, we must develop an attachment for the 5.56-223 firearm and be as minimally invasive as possible. The device will visualize the cardinal directions and track the magazine's remaining rounds. The device will be impact and element resistant and be ambidextrous for left and right-handed users. In order to achieve these requirements, several mechanical and electrical specifications were set forth. On the mechanical side, the device will be military spec consisting of a steel housing. Looking at the electrical components, we are including a 9 degree of freedom measurement unit. This includes an accelerometer, magnetometer, and gyroscope. The device will utilize an RFID reader, an OLED screen, and a rechargeable battery as well.
While updating the final design, we had few changes. We switched from CR123 battery to the 9-volt rechargeable battery and added the 9-volt battery connector, tactile bottoms, drive screws, O-ring, lock nut. The total cost for this project is $344.17. Labor average cost is $94 per hour. So the total cost plus the labor hour cost is $438.17 per hour.
This slide contains our work breakdown structure. The work breakdown structure was used to keep track of pertinent tasks as we progress through the various design stages. Tasks that have been completed are highlighted in green, while in-progress tasks are highlighted in orange. We were unfortunately not able to achieve our end goal of having a version 1.0. Building on the previous slide is our schedule. The original schedule had to be altered to compensate for the changes made in response to coronavirus. Some key takeaways are that the pandemic has caused major setbacks for our design. A functioning prototype could not be completed as a result. A compressed semester also adds a layer of stress for everyone due to the chaos of completing assignments for multiple courses. Under normal circumstances, we would have had a fully functioning prototype. Despite all of these challenges, however, much progress has been made regarding all aspects of the device. We truly believe that the round tracking system has serious potential for future commercialization.
With the aid of a vibration data collection application on a cellular device, multiple activities were done in order to collect a data range of G-force that will be filtered out for our sensor. The image on the bottom right represents sensor placement and orientation of the data collected. The green values will be the focus point of the experiment since they represent rifle kick. The images following this slide contain data collected for multiple situations. Here you can see the different data sets collected at the range that a service member would do while carrying an assault rifle. Notice none of these peaks reach the shot value at 2.8 Gs in the bottom image for the speed reload activity. In this data set, weapon firing was conducted as well as having a different weapon system firing simultaneously with the assault rifle. It can be seen that the alternate weapon system has no effect on the vibration data collection application. As the rate of fire increased, it appeared that the cellular VDC app could not keep up with the data and provide proper feedback to the screen display. For both steady and rapid shot values, the middle shots could not provide a plausible reading. From all the data collected, the range of 2.75 Gs to 3.25 Gs will be used for our sensor to subtract one round.
This video shows how the coding portion of the design will work utilizing LabVIEW software. From test data, it was concluded that a gunshot vibrational amplitude ranges from 2.75 G to 3.25 G of vibration. This video shows in the top left what the OLED screen would display each time it recognizes a vibrational frequency as a gunshot versus noise that will be picked up, such as walking, talking, a nearby gunshot, or the gun dropping.
By using the weight of a loaded rifle with our sensor attached and dropping the weapon system 1 meter, the impact force is calculated out to see if the housing can withstand the impact. The peak values of 1 KSI are visible on the visibility hood of our prototype, which will not fail due to the external components being made of steel.
In order to further improve our design and testing process, it is necessary to obtain a better measurement device to record clearer data. After obtaining more precise and accurate data, we can prototype the device and test the physical components. Future improvements to our design might include the addition of a light sensor for a dimming feature to protect the soldier using the attachment. Another upgrade to be considered is to provide feedback from the device to a command room within a forward operating base, giving a constant ground troop status to military leaders.
ID implemented successfully. Software and hardware are tested and results verified in the previous slides. Surrounding noise will not impact the measurement, so if there was a firing gun nearby or any other noises, it wouldn't affect the measurement. In 6 shots, measurement maximum noise was 2.3 G and 1.6 G. Model impact force is 20.8 pound force. Attempt to improve feedback speed to better handle rapid pace of bullet fire.
We would like to take a moment to thank everyone who helped us along this path. We are sincerely grateful.
Ladies and gentlemen, thank you for your time. Are there any questions?
All right, I'll go first. Okay, I think you guys did a a wonderful job. Considering the circumstances, you guys really. But I do have like how you leverage. You actually did a 3D printed prototype and actually collected. You guys were able to make just the LCD display on the working and try to collect those vibration data and even try to analyze those data through the post-processing using NetView. I think those are all very, very good achievements. So it's for that I just want to compliment you guys. But I do have one quick question. Could anybody help me understand what's the characteristics of the vibration when the gun is fired?
So what exactly do you mean?
Like what kind of characteristics are you looking for?
Okay, so Mason and I can speak to this. We actually had the Coco 80X. I don't know if you're familiar with that or not. Professor Greiner introduced us to it when I was taking one of his courses a couple semesters ago. What we're looking for is let me try to get to the slide here with the data. We're looking for the we're looking to when you fire a round out of a rifle, it is a detonation. There's a charge that detonates and sends the bullet flying down the barrel of the gun and then ultimately downrange. So when that detonation of that powder occurs, it creates vibrational frequencies that reverberate throughout the chassis of the firearm. And then we wanted to take the Coco 80X and figure out what that frequency was, and then use that as our baseline. But unfortunately, the Coco 80X, for some reason, the package that we needed to be able to record the vibrational data was locked. I guess when Wilkes acquired the device, they didn't get the full suite or whatever, so we weren't actually able to use that particular device to do data acquisition. So what we did is Mason and I went and we found these apps that you can just download on the App Store for iTunes, and they are super capable. They actually use the accelerometer that is built into the cell phone. And so what we did was we turned on that app, we zip tied a phone to the side of the rifle, and then we got our data that way. I hope that answers your question.
Well, yeah, absolutely. This is definitely, so basically you guys were able to get the visual, but not the digital data.
Yeah, right. So like the app that we used, it doesn't have any way to like export the data in any kind of like file format.
But you guys are able to be nimble and being creative to find these ways. Again, I have to compliment them for that. So
yeah,
thank you.
Yeah, absolutely. I think Matt hit it well on the head. Like I said, the round is a controlled explosion. Once that firing pin hits the back of the round, it's an explosion inside the upper receiver of the rifle, sends the round downrange. We tried hooking up the Coco 80X. As soon as we hit the VDC software, vibration data collector, it says software not purchased. Please contact your seller.
Understood. Okay. Thanks.
We took the cell phone, strapped up, and did what we had to do.
Any other questions?
I think we put him to sleep.
Nice, very interesting project, actually.
Again, I'm sorry about the whole fiasco trying to share the screen. I usually don't use the I never downloaded the client for Zoom because I read that they were like selling a lot of data and stuff. So I just always did the online client from the browser. But I guess if you want to share sound properly, you have to actually download the app. So I'm sorry about that. It's my fault.
I'm going to ask a silly question again. Sorry for my lack of vibration knowledge. All of those graphs, like the one that you are showing in that kind of in a panel right here, you're referring to numbers like 3 point something G. What is the unit of G? What is that?
G's a force. Basically, when you're like, you ever see those flight simulations that they train like the pilots and whatnot? And they
gravity. Yeah. You mean the gravity?
Yeah, for gravitational acceleration.
So, so that's data from accelerometer, right?
Yeah.
Yes.
Oh, okay. Thank you.
I just want to say something quickly. I mean, you guys all were in my class. I always preach to you guys, as an engineer, you should never be stopped. You always find your way around. So when you work on your senior project, use that mentality. And yes, we are in a very difficult situation right now, but that mentality shouldn't change. We just face different situations, and always try to find a way around it. Don't let those obstacles stop you.
Yeah, exactly. And, you know, kind of tried to touch on it within our slideshow, but, you know, we were all pretty passionate about this project. We were all pretty excited about it. You know, we were really amped to get in there and actually do something that we thought was that was going to be like, we thought we could actually achieve something with this. We thought we were actually going to be able to take this and go somewhere with it. When we were thinking of ideas to do for our senior project design, we actually, we made it a point that we wanted to, you know, we don't want to design something just to design something just to make it so that we could get a grade on our senior projects. We don't want to design something because it's going to be easy. You know, we wanted to go in and we wanted to say, okay, what's something that could actually be beneficial to the world in some way? And then how can we go about and actually bring something to fruition on that? And we were really excited to get going and you know, and work on this project. We had full intentions on getting full working prototypes, and we had big plans. We were going to get like matching t-shirts and wear them in the presentation and stuff like that. But you know, the world got slammed by coronavirus, so it wasn't able to happen. So we just, like I said, we just tried to persevere. And like you mentioned, we just kind of took that attitude and brought it with us. And unfortunately we weren't able to get as far as we wanted to, but we still were able to get some very, very excellent results in every aspect of the project.
I mean, any of you guys, when you work on your senior project, if you want to be a good engineer, you have to feel emotionally attached to your project. You really have to care about, I want to improve this. This is your baby. I mean, you have to feel emotionally attached to your project. You have to care. You have to, I want to do better. I want to, whatever situation is, I want to do a better job.
Absolutely.
Okay. Well, thank you very much, guys. Virtual clap. Well done.
Thank you.
I also applaud your innovation, getting data and this was another team I put on the spot a few weeks ago in class, and they really responded. I said, Sam, you know, learn LabVIEW, get the GUI working. She did, you know. So they did great. Okay, well that's all I got. Let me just do a quick 2-minute wrap up. I know everyone's kind of getting exhausted. I don't know if it's more or less tiring sitting at your computer screen versus sitting in the desks at Stark 101. But thank you to all the teams that presented today. Thank you for all your work for this semester. For the 392 teams, thank you for your work for both semesters, and good luck in the world ahead of you. You know, I'm assuming everyone is graduating this December that's in 392. So congratulations on your time at Wilkes, and thank you to all the advisors. You know, working with them week in, week out, giving them guidance and sharing your knowledge with them. Thank you to faculty for all your questions today, and hopefully to the 391 teams, take these questions to heart. They're not just trying to be mean-spirited or say, you know, they're you know, these are people with many years of experience that have seen teams come and go. So yeah, really reflect on the questions and see how you can use that for the break and going into next semester. Okay, so my faculty colleagues, please get me your grading rubric. Just send me that spreadsheet afterwards today. And to both classes, I'll see you on Tuesday for a more in-depth wrap-up to the semester. So 4 o'clock, the 392 class, 5 o'clock, the 391. I'll see you via Zoom.
Thank you, Ed.
Thank you.
Okay. Thank you, everybody. Have a great weekend.